Why the Great Attractor breaks everything we know about physics. Something massive, something invisible is pulling our entire galaxy, and we have no idea what it is. The Milky Way isn't just drifting through space, it's racing, moving at nearly 600 kilometers per second, drawn toward a hidden force so powerful that it tugs on hundreds of thousands of galaxies around us. We can't see it directly. We don't know exactly what it is, and yet its presence is undeniable. The discovery of the Great Attractor. In the 1970s, when astronomers looked out into the sky, they expected to see a universe that made sense. Galaxies, clusters, and superclusters were all moving according to gravity, flowing outward as the universe expanded from the Big Bang. It was orderly, predictable, a cosmic clockwork. But then, little by little, cracks began to appear in that picture. Vera Rubin, working quietly with her spectrograph, stared at the spiraling arms of distant galaxies and noticed something that didn't add up. The outer stars were moving far too fast, spinning as if invisible hands were tugging on them. At first, it seemed like a quirk of the galaxies themselves, an anomaly to be noted and perhaps explained later. But in time, Rubin's observations became part of a larger puzzle that stretched across millions of light years, a puzzle that no one could ignore. Meanwhile, in other corners of the world, Mark Davis and George Peebles were mapping the motions of entire galaxies. They weren't concerned with the spin of a single galaxy. They were looking at clusters, at the large-scale structure of the universe. Using redshift measurements, they could see how galaxies moved both away from us and relative to one another. And that's when the anomalies appeared. Galaxies were not simply drifting apart as the universe expanded. They were flowing, moving towards something enormous, something invisible. Their paths were skewed. Their velocities defied expectations based on visible matter. These peculiar motions, as astronomers called them, hinted at a force pulling across vast cosmic distances, one that no telescope had yet seen. The anomalies were subtle at first, whispers in the data that could have been dismissed. But as more galaxies were mapped, the pattern became undeniable. It wasn't just a few galaxies misbehaving. It was entire clusters, moving in unison, drawn toward a single hidden point. The universe was revealing a secret, not through light or color, but through motion itself. And the closer astronomers looked, the stranger it became. It was in the 1980s that Margaret Geller and John Huckrow took up the challenge of making sense of this mysterious flow. They weren't just cataloging galaxies. They were trying to map the invisible structure of the universe itself. Using redshift surveys, they measured thousands of galaxies, plotting not just where they were, but how they were moving. Every point on their map was a clue. Every deviation from the expected cosmic expansion was a sign of something massive lurking in the shadows. By tracing these movements, Geller and Huckrow began to see the outlines of a gravitational giant, a force so enormous that it dwarfed every known cluster of galaxies. The discovery didn't happen with a single aha moment. It was a gradual unfolding, a detective story written across millions of light years. Galaxies streamed toward a region hidden behind the plane of the Milky Way, a place we can barely see because of the thick clouds of stars and dust that block our view. This region would come to be called the Zone of Avoidance, and within it lay the first hints of the Great Attractor. Astronomers were essentially seeing the effects of something they could not observe directly. It was a gravitational shadow, revealed only by the way it made everything around it move. Estimates of the mass involved were staggering. Scientists realized they weren't dealing with a single cluster or even a supercluster. This invisible force contained the mass of tens of thousands of Milky Ways, concentrated in a region so vast that the human mind struggles to comprehend it. The scale was mind-bending. Here, in a small corner of the observable universe, was something that could bend the motions of entire galaxy clusters, a hidden architect of cosmic flows. Every new observation only deepened the mystery. Telescopes could peer through the zone of avoidance using infrared and X-ray measurements, confirming that something massive lurked there. But even as data accumulated, the full nature of the Great Attractor remained elusive. Was it dark matter concentrated in ways we hadn't imagined? Was it a collection of massive clusters, hidden by cosmic dust? Or was it something even stranger, something that challenged our understanding of physics itself? As the 1980s turned into the 1990s, the Great Attractor became a central puzzle in cosmology. It was no longer just a curiosity. It was a force that forced astronomers to rethink the structure of the universe. Galaxies were not moving randomly. They were part of a cosmic flow, a motion that spoke to unseen mass, stretching across hundreds of millions of light years. Mapping these flows became an exercise in both patience and imagination. Every redshift, every velocity measurement was a thread in a tapestry revealing the contours of a hidden cosmos. The work of Rubin, Davis, Peebles, Geller and Huckra set the stage for decades of exploration. They showed that the universe was not fully visible, that motion itself could reveal hidden giants, and that even on the largest scales, we were still only beginning to understand the rules of the cosmic game. They discovered not just a gravitational anomaly, but a profound reminder. The universe is stranger than we think, and the things we cannot see often exert the most influence. The Great Attractor did not announce itself with fireworks. It revealed itself slowly, through subtle deviations in the motions of galaxies, through careful measurements taken over years of painstaking observation. And yet its presence is undeniable. Entire clusters of galaxies, including our own Milky Way, are moving in its direction at hundreds of kilometers per second, drawn by a gravitational force we cannot fully see, a shadowy giant that dominates the flow of matter across the cosmos. Even now, decades later, the early work of these astronomers remains vital. Their surveys, their redshift maps, their patient detective work built the foundation for everything we know about large-scale cosmic flows. And what they revealed was far beyond what anyone had imagined. A hidden structure so massive, so influential, that it bends the motions of galaxies across hundreds of millions of light years, shaping the universe in ways we are still struggling to understand. The Great Attractor is more than a mystery. It is a reminder of the limits of human vision and the power of cosmic forces. It is a gravitational enigma, revealed not through light, but through motion, demanding that we pay attention to the universe's subtle whispers. As astronomers continue to map galaxies and trace their flows, the Great Attractor remains a beacon of the unknown, a colossal presence lurking behind the stars, reminding us that the universe is far larger, stranger, and more fascinating than we could ever have imagined. What the Great Attractor is. When astronomers first traced the motions of galaxies toward a single point in space, they realized they were not chasing a star, a nebula, or even a single cluster of galaxies. What they were chasing was something far stranger. The Great Attractor is not an object in the traditional sense. It is a gravitational anomaly, a region in space where the combined pull of mass, both visible and invisible, warps the paths of galaxies across hundreds of millions of light years. It exerts its influence silently, invisibly, shaping the flow of the universe without announcing its presence. Unlike a black hole or a galaxy, the Great Attractor cannot be seen directly. It is a cosmic sculptor, revealed only through the motion it imposes on everything around it. Galaxies do not move at random. They stream, they converge, and their paths converge toward this hidden gravitational well. Observing this flow is like watching leaves swept by an invisible current in a vast river. The current itself cannot be touched or seen, but the motion of the leaves traces its presence. In this case, the leaves are galaxies, and the current is the gravitational pull of the Great Attractor. The Great Attractor lies in a part of the sky astronomers call the zone of avoidance. This is a swath of space that is almost entirely obscured by the dense disk of the Milky Way. From our vantage point on Earth, the light from stars and dust in our galaxy blocks everything behind it, hiding enormous structures from direct observation. Optical telescopes cannot penetrate this cosmic veil, and even the largest visible light surveys fail to reveal what lies beyond. It is here, in this shadowed region, that the gravitational anomaly resides. Infrared and X-ray telescopes can pierce through some of the dust, but only partially. Observations show hints of massive clusters, dense concentrations of galaxies, and regions where dark matter may be tightly packed. Yet even with the most powerful instruments, the full structure remains largely hidden. The Great Attractor is a ghost in the galaxy, a mass whose presence can be measured but not fully seen, a force whose effect dominates its surroundings while remaining out of view. Early observations suggested it might be a single, massive cluster. But as data accumulated, it became clear the Great Attractor is far more complex. It is likely composed of multiple galaxy clusters, filaments of galaxies, and enormous amounts of dark matter, all combining to create an enormous gravitational pull. The mass is staggering. Estimates suggest it is equivalent to tens of thousands of Milky Ways, concentrated across hundreds of millions of light years. This invisible mass doesn't behave like the compact, bright objects we are used to studying. It is spread out, diffuse, and interwoven with cosmic filaments. Galaxy clusters embedded within this anomaly move together, pulled toward the same unseen center. Even our own Milky Way, part of the larger Lania supercluster, is caught in this flow, drifting inexorably toward the gravitational center. The role of dark matter. Much of the Great Attractor's mass is thought to be dark matter, the invisible substance that makes up roughly 85% of the universe's matter. Dark matter does not emit light, absorb it, or interact with normal matter except through gravity, which makes it essentially undetectable by conventional means. Its presence is inferred entirely from the motion of galaxies and clusters around it. In the case of the Great Attractor, dark matter could form massive filaments and knots, creating a gravitational pull strong enough to accelerate entire superclusters toward it. Without dark matter, the visible galaxies alone cannot account for the peculiar velocities observed. The unseen mass, threading through the universe like a cosmic scaffold, is what gives the Great Attractor its overwhelming influence. The zone of avoidance makes the Great Attractor extremely difficult to study. The Milky Way's plane is packed with billions of stars, interstellar gas, and dust clouds that scatter and absorb light. Optical telescopes are blind in this region. Even infrared surveys, which can see through some dust, struggle to capture the full picture. X-ray observations reveal hot gas in clusters, offering some clues, but still only a partial view. Astronomers have to rely on indirect methods. By charting the velocities of galaxies outside the zone of avoidance, they can extrapolate the location and mass of the Great Attractor. Galaxy motions act like a compass, pointing back toward the gravitational center. These cosmic flows reveal the shape of the hidden mass, hinting at clusters, filaments, and concentrations of dark matter that are otherwise invisible. The Great Attractor is not a static object. It is part of the larger cosmic web, interacting with neighboring superclusters, filaments, and voids. Galaxies are streaming toward it, but the structure itself is evolving. Clusters may merge, filaments may shift, and dark matter may reconfigure over billions of years. Its gravitational influence, however, dominates the local universe, guiding the motion of the Milky Way and countless other galaxies along invisible highways of cosmic flow. It is a reminder that the universe is not a static backdrop, but a dynamic, ever-changing arena where invisible forces sculpt the motion of everything we see. The Great Attractor is not a point on a map. It is the force behind the map, the invisible hand guiding the motions of millions of galaxies across unimaginable distances. Thanks to infrared, X-ray, and radio surveys, astronomers have begun to piece together its outline. Massive clusters like the Norma cluster appear to be part of it, acting as visible markers for the greater gravitational structure. Filaments of galaxies, mostly invisible, stretch between clusters, hinting at the true scale of the anomaly. But the heart of the Great Attractor, the core where its mass is densest, remains shrouded in the Milky Way's dust. No telescope has yet captured it directly, and it may be centuries before technology allows us a clear view. Even without seeing it, the Great Attractor's influence is undeniable. It pulls at the Milky Way and its neighbors, shaping the local universe. It demonstrates that the cosmos contains structures far larger, more massive, and more mysterious than anything visible in the night sky. And within that hidden mass may lie answers to some of the universe's most profound questions about dark matter, cosmic flows, and the distribution of matter across the cosmos. The Great Attractor is not a place to visit or a galaxy to catalogue. It is a force, a hidden gravitational engine that dominates the motions of everything around it. And while its full form remains obscured, its power is written across the universe, traced in the movement of galaxies, the bending of cosmic flows, and the unseen scaffolding of dark matter that threads the cosmos itself. How astronomers detect the Great Attractor. The cosmos is a place of astonishing scale, vast beyond comprehension, where light from the farthest galaxies takes millions of years to reach us. And yet, in the midst of this expansive universe, astronomers discovered a gravitational anomaly so massive that it pulls entire clusters of galaxies toward it, bending their motion across hundreds of millions of light years. This phenomenon, known as the Great Attractor, does not reveal itself with light, color, or spectacle. Its presence is hidden behind the dense plane of the Milky Way, obscured by a thick curtain of gas, dust, and stars. Detecting something so massive, yet so invisible, required ingenuity, cutting-edge technology, and a deep understanding of the subtle fingerprints left by gravity in the cosmos. The first step toward understanding the Great Attractor was realizing that motion itself could serve as a clue. Galaxies do not move randomly. When mapped, their velocities reveal patterns that can indicate the presence of unseen mass. It was in these patterns of motion, combined with the application of multiple observational techniques, that astronomers began to detect what no telescope could see directly. One of the most critical tools for peering through the dense plane of the Milky Way is infrared astronomy. Unlike visible light, which is easily scattered and absorbed by interstellar dust, infrared radiation can penetrate these clouds, revealing stars, galaxies, and structures otherwise hidden. In the search for the Great Attractor, infrared surveys became indispensable. The 2-micron all-sky survey, or 2-mass, revolutionized the mapping of the sky in infrared. By scanning the entire sky at wavelengths of 2 microns, astronomers could detect galaxies lying behind the dense dust of the Milky Way. Using 2-mass data, researchers began to chart the positions of thousands of previously hidden galaxies. The patterns that emerged were startling. Galaxies that had never been catalogued in visible light appeared to cluster along the same trajectories inferred from redshift surveys and galaxy motions. These galaxies traced out the contours of the hidden gravitational structure, confirming that the Great Attractor was not a local anomaly, but a massive concentration of mass in the zone of avoidance. Infrared surveys also allowed astronomers to study the density and distribution of galaxies within this obscured region. While individual clusters could be faint and difficult to distinguish, the aggregate light from thousands of galaxies provided evidence for enormous structures, with masses far exceeding any previously known clusters. It became clear that the Great Attractor was not a single object, but a complex ensemble of galaxy clusters, filaments, and unseen mass bound together by gravity. Infrared alone could not reveal the full scale of the Great Attractor. Many of the massive galaxy clusters hidden in the zone of avoidance are filled with hot, diffuse gas that emits X-rays. Observing this X-ray radiation allows astronomers to identify massive clusters even when the stars themselves are obscured. The Chandra X-ray Observatory, launched in 1999, provided unprecedented sensitivity for detecting these hot, diffuse plasmas. By measuring the X-ray emission from clusters, astronomers could estimate their mass, density, and distribution. In particular, clusters such as the Norma cluster, one of the most massive clusters in the region, revealed themselves through intense X-ray emission, despite being hidden behind dense interstellar dust. These observations confirmed that the Great Attractor contains not only galaxies, but also enormous quantities of hot gas, a signature of the immense gravitational wells that bind clusters together. X-ray measurements also allow astronomers to estimate the gravitational mass of clusters independently. The temperature of the gas and its distribution within a cluster can be used to calculate how much mass is required to confine the gas gravitationally. In the case of clusters associated with the Great Attractor, these calculations indicate masses equivalent to tens of thousands of Milky Ways per cluster, pointing toward a cumulative gravitational force far greater than anything previously catalogued. Radio astronomy. Seeing through the dust. Another crucial method for detecting structures hidden behind the Milky Way is radio astronomy. Neutral hydrogen gas, HI, emits radio waves at a wavelength of 21 centimeters, a signal that can pass through dust almost unimpeded. By mapping the distribution of neutral hydrogen, astronomers can detect galaxies that are completely invisible in optical light. Radio surveys of the zone of avoidance have revealed numerous galaxies streaming toward the same gravitational center, inferred from infrared and X-ray observations. Radio telescopes like the Parkes Observatory in Australia have been particularly instrumental, cataloguing hundreds of galaxies previously undetected. The motions of these galaxies, combined with their positions, allowed researchers to reconstruct the mass distribution of the Great Attractor region, showing a coherent flow toward the hidden center. In addition to detecting galaxies, radio astronomy provides velocity measurements through the Doppler effect. By observing the shift in the 21-centimeter line, astronomers can determine how fast each galaxy is moving toward or away from us. These velocities, when compared with the expected expansion of the universe, reveal peculiar motions, the deviations caused by the gravitational pull of the Great Attractor. It is through these subtle distortions that the gravitational anomaly announces itself, even when the object itself cannot be seen. Combining data from infrared, X-ray, and radio observations allows astronomers to construct a three-dimensional map of the Great Attractor region. Each method contributes a piece of the puzzle. Infrared surveys locate hidden galaxies. X-rays identify massive clusters and hot gas, and radio waves reveal motion through neutral hydrogen. Together, they paint a picture of a region dominated by enormous concentrations of mass, stretching across hundreds of millions of light-years. The scale of the Great Attractor is almost incomprehensible. Individual clusters within it can contain thousands of galaxies, each with billions of stars. When combined with the surrounding filaments and intercluster matter, the total mass reaches hundreds of thousands of times the mass of the Milky Way. It is a gravitational powerhouse, exerting a pull so strong that entire superclusters are moving toward it at velocities exceeding 600 kilometers per second. The mass is not concentrated in a single point, but spread across a complex network. Dark matter threads through the region like an invisible web, binding clusters and galaxies together and amplifying the gravitational influence. Estimates suggest that dark matter constitutes the majority of the mass, with visible galaxies and hot gas providing only a fraction of the total gravitational force. The motion of galaxies toward the Great Attractor is perhaps the most dramatic evidence of its presence. Surveys of galaxy velocities show a coherent flow, stretching across millions of light-years, all converging on the hidden mass. This flow is not random, but structured, following filaments and channels that trace the underlying distribution of dark matter. Infrared, X-ray, and radio data all confirm the same pattern. The Milky Way, the Virgo cluster, and countless other galaxies are part of a massive stream moving toward the same gravitational center. The Great Attractor dominates the local cosmic landscape, shaping the trajectories of galaxies and revealing the scale of mass distribution in the universe beyond what is visible. Calculating the total mass of the Great Attractor is a formidable challenge. Direct observation is impossible, so astronomers rely on the combined evidence of galaxy motion, X-ray emission, and large-scale structure mapping. Even conservative estimates place the total mass at hundreds of thousands of times that of the Milky Way, spread over a region hundreds of millions of light-years across. The Norma cluster, one of the densest regions, alone contains mass equivalent to tens of thousands of Milky Ways. When combined with surrounding clusters, filaments, and dark matter, the gravitational pull becomes almost unimaginable. It is a force that bends the motion of galaxies over immense distances, creating the cosmic flow observed across the southern sky. The scale is also staggering in terms of volume. The Great Attractor spans a region that covers a significant fraction of the local supercluster. Unlike compact clusters, its influence is diffuse yet pervasive. Galaxies, thousands of light-years apart, respond to its gravity, forming streams and filaments that converge on the hidden mass. It is a structure whose size and mass are almost impossible to visualize, yet whose existence is clearly written in the motion of the universe itself. Despite the progress made with infrared, X-ray, and radio astronomy, much of the Great Attractor remains invisible. The zone of avoidance prevents a direct optical view, and even the most powerful telescopes can only infer its structure. This forces astronomers to become detectives, using the motion of galaxies and the distribution of hot gas as indirect evidence. Each new survey, each new observation adds clarity to a picture that is still largely hidden behind our own galaxy. Through these methods, the Great Attractor reveals itself as a complex, massive, and invisible force. It is a combination of galaxy clusters, filaments, hot gas, and vast quantities of dark matter, exerting gravitational influence across hundreds of millions of light-years. The scale and mass are staggering, dwarfing every known cluster and dominating the motion of the local universe. Even though it cannot be seen in conventional light, its fingerprints are everywhere, in the peculiar velocities of galaxies, in the streams traced by infrared surveys, in the hot gas detected by X-rays, and in the neutral hydrogen mapped by radio waves. The Great Attractor is not a single object. It is a huge gravitational engine, hidden from view, yet shaping the cosmos on the largest scales humanity has ever observed. How the Great Attractor breaks physics. Imagine standing on Earth and watching the stars above. You can see their light, their patterns, and you assume that the universe behaves the way you expect. Gravity pulls, mass attracts mass. Galaxies drift with the flow of expansion, and everything should make sense if you know the mass that's out there. But the universe has a way of mocking those assumptions. Somewhere, behind a wall of dust and stars, there is a force so immense, so invisible, that it drags entire galaxies across space at speeds that don't fit with anything astronomers expect. This is the Great Attractor. At first glance, it seems simple. A region of mass that pulls everything toward it, but when scientists began to measure the motions of galaxies, the numbers didn't add up. The galaxies weren't moving according to the mass we can see. They were moving faster, in strange directions, almost as if an invisible hand were tugging on them with far more force than all the visible stars, gas, and clusters in the region could account for. These motions, known as peculiar velocities, challenged the very foundations of physics as we know it. Peculiar velocity is the term astronomers use for how a galaxy's motion deviates from the expected expansion of the universe. Every galaxy is supposed to recede from us due to the universe stretching, a motion described by the Hubble flow. But the Milky Way, along with the surrounding clusters, is moving toward the Great Attractor at nearly 600 kilometers per second. That's far faster than what would be expected if only the visible mass in the area were pulling it. And the more galaxies we observe, the more these deviations appear, forming a pattern that no known distribution of matter can fully explain. Imagine throwing a ball and expecting it to follow a straight line, but instead it curves unpredictably toward an invisible force. Now imagine that happening across hundreds of millions of light years, with galaxies instead of balls. This is exactly what astronomers saw. Redshift surveys, infrared observations, X-ray measurements, and radio mapping all confirmed the same thing. Galaxies are moving in ways that violate our predictions. The local distribution of visible mass cannot account for these flows. The numbers don't match up. Something else must be out there. The possibility of hidden mass. One obvious answer is dark matter. Dark matter is invisible. It doesn't emit or absorb light. You cannot see it with telescopes, but its gravity is real. Perhaps the Great Attractor contains an enormous amount of dark matter, far more than in any cluster we've observed. That would explain the strange velocities. The problem is, even accounting for dark matter, the numbers still strain the limits of our models. The mass needed to pull galaxies this fast in this pattern is extraordinary. It's hundreds of thousands of times more massive than the Milky Way, spread across an area so large that our understanding of galaxy clustering and cosmic flows starts to falter. And then there's the stranger possibility. Maybe it isn't just dark matter. Maybe the Great Attractor is a hint that our physics is incomplete, that there are forces or particles we don't yet know. Some theories suggest exotic forms of matter or modifications to gravity that could account for these motions. But so far, no model fits perfectly. The Great Attractor refuses to behave the way standard physics predicts. It challenges assumptions that seemed unshakable just decades ago. The discovery of the Great Attractor doesn't just change how we think about a cluster or a supercluster. It has enormous implications for cosmology, the study of the universe as a whole. For decades, scientists have assumed that the universe is homogeneous on large scales. Matter may clump locally, but across hundreds of millions of light-years, everything should average out. Gravity should balance with the expansion of the universe. Galaxies should roughly follow the Hubble flow, drifting away from each other at predictable speeds. But the Great Attractor defies that assumption. It creates a local gravitational anomaly so strong that it dominates the motions of galaxies across the southern sky. The velocities observed are inconsistent with the predictions from the visible universe and even from standard dark matter models. This means that local gravity is more chaotic and uneven than previously thought. Cosmic flows aren't smooth. They're warped by hidden giants like the Great Attractor. If such massive anomalies exist, it raises a question. Are there more of them lurking behind dust and stars, in regions we cannot see? Are we just scratching the surface of a hidden network of mass that sculpts galaxy motion on scales we have barely begun to map? And if these forces are so strong locally, how do they interact with the universal expansion? The expansion of the universe is supposed to push galaxies apart. Yet here is a hidden force pulling them together at speeds that defy the expected balance. Gravity is one of the best understood forces in physics. Newton gave us a simple equation. Einstein expanded it with relativity, and for centuries it has accurately predicted the motion of planets, stars, and galaxies. But the Great Attractor exposes cracks in even these well-tested models. The observed velocities of galaxies suggest that either there is unseen mass concentrated in ways we cannot detect, or that gravity behaves differently on these enormous scales. Some scientists have proposed modifications to the law of gravity. Maybe gravity doesn't weaken with distance in the exact way we expect when measured across hundreds of millions of light-years. Maybe there is an unknown component, a fifth force, subtly altering galaxy motion in ways we cannot yet measure. Each hypothesis is tested against the data, and each time, the Great Attractor seems to push the limits, showing that our understanding of gravity may be incomplete when applied to such vast cosmic structures. This isn't a minor discrepancy. The scale of the anomaly is immense. If the mass distribution is fully responsible, it implies concentrations of matter far beyond any known cluster. If gravity itself is being modified, it suggests that the fundamental laws of physics might require adjustment on intergalactic scales. Either scenario shakes the foundation of modern cosmology. Dark matter or something more exotic. While dark matter is the leading explanation, the Great Attractor teases the imagination. The velocities of galaxies hint at the possibility of unseen structures, hidden masses, or exotic forms of matter that are even stranger than what current models predict. Could there be concentrations of matter in forms we cannot yet detect? Could there be massive filaments or knots of dark matter threading through space beyond the reach of our instruments? Some theorists even speculate about exotic physics, modifications of general relativity, the presence of dark energy in localized regions, or even unknown particles that interact only gravitationally. The data is tantalizingly precise, yet frustratingly incomplete. Every galaxy measured adds to the puzzle, but no single observation can fully explain the scale and strength of the pull. The Great Attractor behaves like a force from a hidden dimension, revealing its presence only through motion. The Great Attractor also forces astronomers to reconsider the relationship between local gravitational forces and the overall expansion of the universe. On large scales, the universe is expanding. Space itself stretches, carrying galaxies away from each other. But here is a force that counteracts that expansion, pulling entire superclusters in a single direction. It demonstrates that expansion and local gravity are in constant tension, and that enormous local anomalies can dominate motion even as the universe grows larger. It raises deeper questions. How uniform is the universe on the largest scales? Are there more gravitational anomalies like the Great Attractor, hidden behind dust, waiting to bend cosmic flows in ways we cannot yet measure? And if so, does this challenge our assumption that the universe is smooth and homogeneous when viewed across hundreds of millions of light years? The Great Attractor suggests that the cosmos is far messier, far more dynamic, and far more unpredictable than we have assumed. One of the most frustrating aspects of the Great Attractor is how hidden it is. Astronomers can only infer its existence through the motion of galaxies. Telescopes cannot see it directly in visible light. Infrared, X-ray, and radio astronomy provide partial glimpses, revealing clusters, filaments, and hot gas. But the heart of the anomaly remains shrouded in the zone of avoidance. Its mass is real, its influence undeniable, yet its full structure remains elusive. This limitation forces scientists to work with indirect evidence, piecing together a picture from velocities, redshifts, and radiation at wavelengths that can pierce the Milky Way's dust. Every observation confirms that something massive dominates the region, but the details are sketchy. We know its pull, we can trace the cosmic flow, but the hidden mass that drives it remains mostly invisible, like a ghost sculpting the motion of the universe from the shadows. The cosmic puzzle. The Great Attractor is more than a single anomaly. It is a window into the unknown, the peculiar velocities of galaxies, the unseen concentrations of mass, the tension between local gravity and universal expansion. All these factors challenge our standard models. They hint that the universe may contain forces or structures that lie beyond our current understanding. It is not just a problem of numbers or calculations. The Great Attractor forces us to question the assumptions underlying cosmology, that gravity behaves consistently at all scales, that mass is distributed in predictable ways, and that the expansion of the universe dominates motion on large scales. The data refuses to fit neatly into these assumptions. The galaxies speak a language of motion that does not conform, whispering of unseen mass, strange physics, and cosmic flows that defy expectation. Even with decades of observation and sophisticated instruments, the Great Attractor remains a puzzle. Its mass is vast, hundreds of thousands of times that of the Milky Way. Its scale is immense, spanning hundreds of millions of light years. Its influence bends the paths of galaxies, pulling them faster and differently than physics predicts. It is a gravitational anomaly that forces astronomers to rethink everything they know about the structure, motion, and composition of the universe. The Great Attractor and dark flow. The Great Attractor is already strange enough on its own. Galaxies are moving toward it at hundreds of kilometers per second, yet the mass we can see cannot fully explain why. But the mystery doesn't stop there. Beyond the zone of avoidance, beyond the clusters and filaments astronomers can map, there is a pattern in the motion of galaxies that hints at something even more extraordinary: dark flow. Dark flow is the term scientists use to describe the unexpected coherent motion of galaxy clusters in a direction that seems to point beyond the observable universe. While the universe expands in every direction, pushing galaxies apart, some clusters appear to move as if pulled by a gravitational source that cannot be seen and might even lie outside the horizon of what we can observe. This motion is subtle but consistent. Hundreds of clusters, scattered across billions of light years, all drift toward a point in space that we cannot detect with any telescope. The connection to the Great Attractor is tantalizing. Both phenomena involve galaxies moving in ways that challenge standard cosmology. The Great Attractor dominates the local cosmic neighborhood, creating peculiar velocities that defy the mass distribution we know. Dark flow suggests that this kind of gravitational pull may not be limited to our local universe. It raises the possibility that structures beyond what we can see, maybe entire superclusters, massive concentrations of dark matter, or something more exotic, are influencing the motion of galaxies we can observe. Astronomers have spent years trying to quantify dark flow. Using precise measurements of the cosmic microwave background, CMB, they examine the tiny variations in temperature caused by the movement of galaxy clusters. When a cluster moves relative to the CMB, it slightly shifts the temperature of the photons passing through it, a phenomenon called the kinematic Sunyaev-Zeldovich effect. By analyzing hundreds of clusters, researchers detect a subtle but consistent motion that cannot be explained by known mass alone. The numbers hint at a pull extending far beyond the Great Attractor, perhaps stretching beyond the limits of the observable universe itself. QE, the Great Attractor, and dark flow are not the only cosmic anomalies that challenge our understanding. Across the universe, astronomers have observed phenomena that seem to defy expectations and hint at forces or structures that remain hidden. Cosmic microwave background anomalies are one example. The CMB is the afterglow of the Big Bang, a nearly uniform sea of radiation filling the universe. It should be smooth, with only tiny fluctuations caused by the distribution of matter early in cosmic history. Yet, high-precision observations, particularly from the WMAP and Planck satellites, reveal strange patterns, unusually large temperature variations, alignments that stretch across the sky, and features that appear too coherent to fit standard cosmological models. These anomalies may be random, or they could hint at unseen structures beyond the observable universe, similar to the unseen mass that drives the Great Attractor. Supervoids are another enigma. These are vast regions of space with far fewer galaxies than expected, sometimes hundreds of millions of light-years across. The largest supervoids create cold spots in the CMB, areas where radiation appears cooler due to the lack of mass to gravitationally pull it. These structures are difficult to explain with conventional models of galaxy formation and distribution. Their sheer size and coherence suggest that the universe is more irregular than we expect, that enormous regions of mass and empty space can create gravitational effects that ripple across enormous distances. Fast radio bursts add another mystery. These are extremely short but intense flashes of radio waves coming from distant galaxies. Some appear to repeat, some do not, and their origins are still largely unknown. What is remarkable is their distribution and intensity, which hint at massive energies at play, potentially involving exotic physics or extreme gravitational environments. While FRBs are not directly linked to the Great Attractor, they demonstrate that the universe is full of phenomena that challenge existing models, where observed behavior doesn't match predictions based on known physics. The Great Attractor, dark flow, CMB anomalies, supervoids, and FRBs may all be different pieces of the same puzzle. They reveal a universe that is far more complicated and chaotic than our models suggest. Each phenomenon points to the presence of hidden structures, forces, or forms of matter that we cannot see directly. The Great Attractor shows this locally, within a few hundred million light-years. Dark flow hints that this might extend across billions of light-years. Cosmic microwave background anomalies suggest that the early universe itself may have been influenced by unknown structures. Supervoids show that matter is distributed unevenly on enormous scales. Fast radio bursts hint at energetic processes or hidden conditions that we do not fully understand. In a sense, the Great Attractor is a small-scale preview of a much larger mystery. It is the closest, most accessible example of an invisible gravitational force shaping the universe, giving astronomers a laboratory to study how mass and motion interact in ways that break conventional expectations. Dark flow and other anomalies take the mystery further, hinting that these invisible forces may extend beyond our observational limits, shaping the universe in ways we cannot yet measure. When considering the Great Attractor alongside dark flow, the scale of what might be influencing galaxy motion becomes staggering. The Great Attractor alone contains mass hundreds of thousands of times that of the Milky Way. Dark flow, if confirmed, implies influences from scales that dwarf even that, potentially involving structures beyond tens of billions of light-years. For comparison, supervoids can span hundreds of millions of light-years, creating gravitational effects on surrounding galaxies, while the anomalies in the cosmic microwave background stretch across the observable universe, hinting at coherent patterns too large to arise from normal galaxy formation. These phenomena force astronomers to confront the limits of observation. The universe we see is only a fraction of what might exist. The motion of galaxies, the cold and hot spots in the CMB, the gaps in galaxy distribution, and mysterious bursts of energy all suggest that much of the universe's mass and structure remains hidden. Whether obscured by dust, stretched across vast distances, or composed of forms of matter and energy we cannot detect directly. What it means for physics. Taken together, the Great Attractor, dark flow, and other anomalies reveal cracks in our understanding of gravity, motion, and cosmic structure. Peculiar velocities and coherent flows challenge the idea that mass is distributed uniformly enough for standard models to predict motion accurately. They suggest the existence of hidden mass on scales far beyond what we have catalogued. They also raise the possibility that gravity may behave differently on the largest scales, or that unknown forms of matter or energy are at play. Each new observation forces a re-evaluation. Are the anomalies the result of unseen dark matter, or is something more exotic shaping the universe? The evidence grows with each survey, yet definitive answers remain elusive. The Great Attractor is the first clue, the closest evidence of an invisible gravitational force. Dark flow hints that it may be part of a larger cosmic architecture, stretching far beyond our ability to see. CMB anomalies and supervoids suggest that these forces have been shaping the universe since its earliest moments. Even as astronomers map galaxy velocities with increasing precision, they continue to uncover patterns that defy expectation. The Great Attractor, dark flow, supervoids, and cosmic microwave background anomalies are not isolated oddities. They are signs that the universe is full of hidden structure, that gravity can act on scales far beyond what we have directly measured, and that matter and energy may exist in forms or distributions we do not yet understand. These phenomena are connected not by simple cause and effect, but by their shared defiance of expectation. Each challenges our models, each forces new questions, and together they hint at a universe that is more complex, more massive, and more mysterious than any single observation can reveal. The motions traced by galaxies toward the Great Attractor, and potentially beyond through dark flow, show that the universe is not just expanding. It is sculpted by massive unseen forces that warp the paths of stars, clusters, and superclusters. It is a universe where the visible is only a small fraction of the whole, and where motion itself may reveal truths that light cannot. How astronomers measure the Great Attractor. The Great Attractor is not an object you can see with a telescope. It does not shine, glow, or reflect light. Its presence is felt through the movement of galaxies across space. Measuring it requires more than pointing a lens at the sky. It requires reading the invisible fingerprints it leaves on the universe, tracing the motion of galaxies, and mapping how the cosmos itself bends under its immense pull. The first step in this cosmic detective work comes from redshift surveys. Every galaxy is moving, and its light carries the story of that motion. Light from a galaxy moving away from us stretches, shifting toward the red end of the spectrum. This is the familiar Doppler effect, the same phenomenon that makes a siren sound lower as an ambulance drives past. In the vastness of space, redshift tells us how fast a galaxy is moving relative to Earth. By measuring redshifts across hundreds of thousands of galaxies, astronomers can create maps of motion, revealing flows that cannot be explained by the universe's expansion alone. Galaxies are not simply drifting apart, they are moving in coordinated ways, pulled towards something invisible. The Great Attractor makes its presence known through these deviations, tiny but measurable shifts in speed and direction. Creating these maps is like piecing together a three-dimensional puzzle. Each galaxy's redshift is a clue, a single arrow showing where it is moving. When thousands of arrows are plotted across the sky, a pattern emerges. Galaxies appear to stream along invisible highways, converging toward a hidden center. These are cosmic flow maps, showing the invisible currents that guide galaxy motion over hundreds of millions of light years. These maps are complemented by velocity field charts, which quantify how much each galaxy deviates from the expected motion caused by universal expansion. A galaxy that should be moving at a certain speed because of the Hubble flow may be moving faster or slower, or in a slightly different direction. These differences are measured and displayed as vectors, arrows that trace the flow of matter through space. In these charts, the influence of the Great Attractor becomes clear. It dominates the motion in its region, drawing clusters, groups, and individual galaxies toward its hidden mass. The process of measurement is painstaking. Light from distant galaxies is faint, often distorted by dust and intervening objects. Instruments must separate the tiny redshift signals from background noise. Data from different wavelengths, optical, infrared, radio, is combined to create a coherent picture. Infrared surveys can detect galaxies hidden behind dust, radio waves trace neutral hydrogen, and optical observations capture the brighter galaxies. Each method fills in pieces of the puzzle, and when combined, they reveal the scale and direction of motion with remarkable precision. Redshift surveys also allow astronomers to estimate distances, which are crucial for understanding how much mass is required to cause the observed motion. The farther away a galaxy is, the more subtle its motion relative to the cosmic expansion becomes. By comparing observed velocities with predicted motion from known mass, astronomers can identify anomalies, the galaxies moving too fast, or along paths that should be impossible based on visible matter alone. These anomalies point directly to the hidden gravitational pull of the Great Attractor. Velocity field charts go beyond simple speed measurements. They reveal the structure of the flow. Instead of uniform movement, galaxies follow streams that converge, twist, and stretch across space. These streams trace the underlying distribution of mass, both visible and invisible. In essence, they act as a map of the gravitational landscape. Peaks in these fields correspond to massive clusters, while valleys may indicate supervoids or low-density regions. The Great Attractor is the most prominent peak in the local flow field, its influence reaching across hundreds of millions of light-years. To make these measurements, astronomers combine thousands of individual observations into massive datasets. Redshift surveys, like those of the 1980s and beyond, catalog hundreds of thousands of galaxies, measuring their speeds and positions with incredible accuracy. Each measurement adds to the flow map, refining the picture of how the local universe is moving. The resulting charts are not static. They are dynamic, showing the collective motion of matter as it responds to the invisible gravitational forces shaping the cosmos. Advanced techniques involve statistical analysis of the velocities. By comparing the observed distribution of galaxy motion with models of mass distribution, astronomers can infer where hidden mass must be located to create the flows they see. This is how the Great Attractor was first pinpointed, through a combination of careful measurement, large-scale mapping, and the recognition that the local universe was moving in ways that could not be explained by visible matter alone. The measurement process also incorporates distance indicators beyond redshift. For galaxies relatively close to us, standard candles like Cepheid variables or supernovae provide independent checks on distances. These measurements help calibrate the velocity field, ensuring that observed peculiar motions are not artifacts of misestimated distances. When the velocities of many galaxies are combined with these distance indicators, the pattern of motion toward the Great Attractor becomes undeniable. Cosmic flow maps are particularly revealing because they show that the motion is not chaotic but coherent. Galaxies hundreds of millions of light-years apart move in roughly the same direction. This coherence is impossible to explain without a massive, concentrated gravitational source. By visualizing the flow, astronomers can trace the invisible structure, almost like watching a river carve a path through a foggy landscape. The galaxies act as tracers of the underlying gravitational field, revealing the presence of mass that cannot be seen directly. Mapping these flows also allows for estimates of the Great Attractor's mass and extent. By analyzing how strongly galaxies are being pulled, astronomers can calculate how much mass is required to produce the observed velocities. These calculations consistently reveal a mass far greater than any individual galaxy cluster, spread across hundreds of millions of light-years. It is a diffuse but immense structure, composed of galaxy clusters, filaments, and vast amounts of dark matter, all of which combine to create the gravitational pull that dominates the local cosmic flow. Observational methods continue to evolve. Modern surveys employ infrared, radio, and X-ray data to fill in gaps left by optical surveys. Infrared observations penetrate dust, revealing hidden galaxies. Radio mapping of neutral hydrogen captures galaxies invisible in other wavelengths. X-ray detection identifies massive clusters through their hot gas, offering additional clues to the mass distribution. Each method is a layer in the three-dimensional map, allowing astronomers to trace not just the motion of galaxies, but the structure of the hidden mass that drives that motion. The measurement of the Great Attractor is also an exercise in patience and precision. Data must be carefully calibrated, corrected for observational biases, and cross-checked across multiple surveys. Even small errors in velocity measurement can dramatically change the inferred mass distribution. By combining millions of data points, astronomers gradually refine their maps, producing ever more accurate representations of the local flow field. The result is a portrait of a region of space that is invisible in light, but unmistakable in motion, a gravitational behemoth that shapes the paths of galaxies across vast distances. Velocity field charts also reveal the complexity of the structure. The flow toward the Great Attractor is not uniform. It shows twists, convergences, and branching paths. These patterns indicate that the mass is spread across multiple clusters and filaments rather than concentrated in a single point. Galaxies respond to the collective gravity of the region, moving along the lines of least resistance, forming streams that highlight the underlying scaffolding of matter. The charts are both maps and motion pictures, showing the universe in action, sculpted by gravity over billions of years. Redshift surveys provide another critical insight: the limits of our observation. While the Great Attractor dominates local flows, there are hints of even larger structures beyond, influencing motion on scales we cannot fully measure. The coherent patterns of galaxy velocities suggest that the Great Attractor is just one peak in a landscape of hidden mass, part of a cosmic web that extends beyond our current observational reach. The measurement of these motions is therefore not just a study of a single structure, but a window into the larger architecture of the universe. By tracing the velocities of galaxies, astronomers can also detect peculiar motion anomalies, deviations from what would be expected even with a known mass distribution. These anomalies are critical for understanding the scale and complexity of the Great Attractor. They indicate regions where mass is unevenly distributed, where dark matter may be concentrated, or where the structure of the flow is influenced by neighboring filaments and clusters. Each anomaly provides a clue, helping to refine the maps and deepen the understanding of the hidden gravitational landscape. The cinematic nature of this work comes from the scale and elegance of the patterns revealed. These maps do not show stars or light, they show motion. They reveal rivers of galaxies, currents and eddies converging on an invisible source. The data is both abstract and tangible. Abstract in that it represents invisible mass, tangible in that it produces observable motion across the cosmos. These flow maps transform the invisible into something almost visible, a portrait of a hidden force that moves everything around it. Even in the era of powerful telescopes and space observatories, redshift surveys and velocity field charts remain the most direct tools for measuring the Great Attractor. They are the instruments that reveal its presence, allowing astronomers to see with motion rather than light. Through them, the invisible becomes known, the impossible becomes measurable, and the Great Attractor emerges not as a point in space, but as a force, shaping the universe in ways that challenge understanding and inspire curiosity. Gravitational lensing and the invisible universe. The universe has a way of hiding its secrets in plain sight. Light travels across billions of light years, straight in empty space, until it passes near a massive object. Mass bends space, mass bends light. Gravity, in all its invisible power, warps the path of photons traveling from distant galaxies, subtly altering their direction before they reach us. This effect, called gravitational lensing, turns the cosmos into a natural observatory, revealing mass that cannot be seen. Gravitational lensing is the universe's way of leaving footprints. The Great Attractor, though invisible in light, reveals its presence through the way it bends light from galaxies behind it. When astronomers map the distortions, they trace the unseen mass. The effect is subtle. Images stretch, arcs appear, shapes skew. But when measured across thousands of galaxies, the pattern becomes unmistakable. These distortions are not random. They point toward concentrations of mass, revealing the skeleton of the hidden universe. Some light paths bend only slightly, creating small distortions called weak lensing. Others pass extremely close to a massive object, producing dramatic arcs or even multiple images of the same galaxy, known as strong lensing. Both phenomena serve as cosmic fingerprints, marking where gravity is strongest. The Great Attractor does not shine in visible light, but it bends space enough that galaxies behind it appear distorted, their shapes whispering the story of an immense gravitational pull. Astronomers measure these distortions with high-precision imaging. They compare the observed shape of distant galaxies with the expected shape if there were no bending. The difference, the shear in the images, indicates the amount of mass in the intervening space. Hundreds of thousands of galaxies contribute to these measurements, creating maps of invisible mass, revealing clusters, filaments, and superclusters otherwise hidden behind the veil of our galaxy. Lensing has a cinematic quality to it. Light from galaxies, billions of light years away, twists and arcs, forming patterns that appear almost artistic, yet they are evidence of physics in action. In these cosmic distortions, the Great Attractor emerges not as a single point, but as a massive region, sculpting the motion of space and bending the light that passes through it. These lensing maps complement velocity measurements, confirming the existence of enormous concentrations of unseen mass. Yet gravitational lensing is not straightforward. Measuring these distortions requires patience and precision. Distant galaxies are faint, their light weak, often blurred by intervening gas, dust, and the atmosphere. Instruments must resolve tiny changes in shape, fractions of a percent, to infer the mass responsible. Statistical analysis is critical. Individual distortions may be small or ambiguous, but patterns emerge when thousands or millions of galaxies are analyzed together. It is like watching ripples on a pond and deducing the shape of an invisible stone dropped in the water. The challenge intensifies in the zone of avoidance, where the Great Attractor lurks. The plane of the Milky Way is thick with stars, dust, and gas, blocking visible light and scattering infrared and radio waves. Lensing measurements must correct for these obstructions. The signal is weaker, contaminated by foreground objects, and much of the sky is obscured. Each observation comes with uncertainties. Is the distortion caused by the hidden mass behind the dust, or by an intervening galaxy in the foreground? Sophisticated algorithms separate the foreground from the background, peeling away layers of interference, but the results always carry a margin of error. Errors and uncertainties are part of the story. Distance measurements are never perfect. Light from a distant galaxy may be reddened by dust, stretching wavelengths and creating confusion in velocity calculations. The exact amount of bending depends on the precise alignment of galaxies along the line of sight, the distribution of mass along the path, and the contribution of smaller structures that may interfere with the main lensing signal. The more complicated the region, the more uncertainties grow. The Great Attractor, sitting behind the densest plane of the Milky Way, is one of the most difficult structures to measure in the universe. Statistical errors are compounded by cosmic variance. The universe is not uniform. Mass clumps unpredictably on all scales. Even if the lensing signal is measured perfectly in one patch of the sky, it may not fully represent the broader structure. Each map is a sample, a window through which astronomers glimpse a much larger and more complex reality. The Great Attractor's mass may be unevenly distributed across clusters and filaments, and lensing observations must account for this patchwork to avoid overestimating or underestimating the total gravitational influence. Instrumental limitations add another layer of complexity. Telescopes and detectors have finite resolution and sensitivity. Tiny errors in calibration can propagate through the measurements, creating apparent distortions that mimic gravitational lensing. Astronomers must separate true cosmic bending from instrumental artifacts, a process that requires repeated observations, cross-checks with different telescopes, and meticulous data analysis. The faint signature of the Great Attractor emerges slowly, confirmed only after years of careful observation. Even with all these challenges, lensing remains one of the most powerful tools to study hidden mass. Unlike redshift surveys, which infer mass from motion, lensing measures the mass directly through its effect on light. It is independent of the speed of galaxies, independent of assumptions about dark matter distribution. When lensing maps reveal concentrations of mass aligned with regions of anomalous galaxy motion, the evidence for the Great Attractor becomes overwhelming. Errors and uncertainties, while frustrating, also shape the way astronomers approach the problem. Every measurement is treated with skepticism and rigor. Data is tested against multiple models, cross-referenced with other observations, and refined over time. Regions that are heavily obscured or sparsely sampled are flagged, and conclusions are drawn cautiously. In this way, the difficulty of measurement does not weaken the discovery, it strengthens it. Only a massive, coherent structure could create a lensing signal detectable through the dense, dusty plane of the Milky Way. Lensing also reveals unexpected complexity. The Great Attractor is not a uniform blob of mass. Instead, it is an intricate tapestry of clusters, filaments, and dark matter, all contributing to the overall gravitational pull. Some regions bend light more strongly, forming visible arcs. Others contribute subtly, detectable only through statistical analysis. Mapping these variations requires not just observation, but imagination, imagining how invisible mass threads through the universe, shaping the paths of light and motion in ways that are difficult to perceive, but impossible to ignore. The uncertainties highlight how much of the universe remains hidden. Every distorted galaxy image, every subtle arc, is a clue to mass that cannot be seen. Lensing shows that the Great Attractor is not a single compact object, but part of a larger network of unseen structures. This network may extend farther than current observations can measure, hinting at additional anomalies and forces shaping the motion of galaxies across the cosmos. Observing gravitational lensing through the zone of avoidance is like trying to read a message written on foggy glass while someone shakes the pane. Light is distorted, obscured, and weakened. But patterns persist. With enough data, the invisible mass reveals itself. The Great Attractor's gravitational signature emerges in maps showing the cumulative effect of millions of galaxies, their shapes skewed just enough to reveal the presence of hundreds of thousands of times the mass of the Milky Way. The cinematic power of lensing lies in its visualization. Light from distant galaxies arcs and stretches across space, forming patterns that can be displayed as glowing maps. These maps trace mass in ways that are otherwise impossible to see. The invisible becomes almost tangible. Clusters appear as bright knots in the distortion field, filaments as threads connecting them, and voids as empty gaps. The Great Attractor stands out as the largest, most dominant feature in the local lensing landscape, a hidden titan bending the cosmos. Uncertainty does not diminish the impact, it amplifies it. Every correction, every adjustment, every careful separation of foreground and background highlights the challenge of measuring a structure that is invisible, immense, and hidden behind dense cosmic dust. The Great Attractor is not just massive, it is elusive, teasing astronomers with subtle hints that require ingenuity and precision to interpret. Gravitational lensing and its uncertainties also show the limits of human observation. The universe is vast, its mass distributed across scales that stretch beyond imagination. The Great Attractor is only one example of how much remains hidden, revealed only indirectly through its influence on light and motion. Every arc, every skewed galaxy, every faint distortion tells a story of forces shaping space that cannot be seen directly, but whose effects are unmistakable. Through lensing, astronomers can piece together this hidden structure, mapping the invisible threads of gravity that govern the motion of galaxies. Errors and uncertainties remain, but they are part of the process. Signposts guiding scientists through the murky zone of avoidance, helping them separate reality from illusion, and slowly revealing the shape of a gravitational force that dominates the local universe. The Great Attractor, traced through light bending and distorted images, emerges not as a singular point, but as a vast, complex structure. Its mass is spread across clusters, filaments, and unseen dark matter. Its influence reaches across hundreds of millions of light-years, bending light and motion alike. Gravitational lensing transforms invisible mass into observable patterns, revealing one of the universe's most mysterious and powerful forces. The role of dark matter and unknown physics. The universe is full of mysteries, and the Great Attractor is one of the most perplexing. It exerts a gravitational pull so strong that entire clusters of galaxies move toward it at hundreds of kilometers per second. And yet, when astronomers look at the light emitted by stars, galaxies, and gas, they cannot account for the mass needed to create such motion. The visible universe, the glittering galaxies, the luminous clusters, the interstellar gas, is only part of the story. Something unseen is pulling at everything around it, something invisible. That something is likely dark matter, the shadowy substance that does not emit, absorb, or reflect light. Dark matter dominates the mass of galaxies and clusters, shaping the formation of cosmic structures from the smallest dwarf galaxies to the largest superclusters. It cannot be seen directly, yet its gravitational influence is undeniable. Without dark matter, galaxies would not rotate as they do. Clusters would not hold together, and the Great Attractor would not have the immense pull it exerts across hundreds of millions of light-years. The concept of dark matter is straightforward in its logic, though extraordinary in its implications. Galaxies move as if they are embedded in a massive halo of unseen mass. Light from distant objects bends around massive structures, revealing invisible mass concentrations. The peculiar motion of galaxies toward the Great Attractor fits this pattern. The visible mass in stars and gas is simply not enough to account for the gravitational pull. Dark matter fills the gap. Its distribution is uneven, concentrated in clusters and filaments, forming a hidden scaffolding for the visible universe. Gravitational lensing provides a powerful confirmation. Light from galaxies behind massive structures twists and arcs, betraying the presence of mass that cannot be seen. The Great Attractor, traced through these distortions, is far more massive than the sum of the stars and gas it contains. The observed lensing effects match what would be expected if large amounts of dark matter were concentrated in clusters and filaments within this region. Its pull is not generated by a single object, but by a vast, interconnected network of unseen mass, moving galaxies along invisible currents. Yet dark matter is not the only possibility. The universe may be stranger than even dark matter suggests. Some scientists consider that gravity itself might behave differently on the largest scales. The motions observed around the Great Attractor could point to modifications in our understanding of how gravity works, especially over hundreds of millions of light years. One such framework is called MOND, or Modified Newtonian Dynamics. In this model, the law of gravity changes at very low accelerations, the kind experienced by galaxies and clusters far from other massive bodies. MOND was originally proposed to explain why galaxies rotate faster at their edges than visible mass alone would allow. If gravity behaves differently in the low acceleration regime, the anomalous motion of galaxies toward the Great Attractor could be a natural consequence. The pull would not come from unseen mass, but from a change in the rules themselves, a bending of the fundamental law that governs motion across cosmic scales. MOND and similar modified gravity theories offer elegant solutions in some cases, but they struggle with the full picture. Galaxy clusters, lensing maps, and cosmic flows suggest mass concentrations that exceed what modified gravity alone can explain. The Great Attractor is not just a minor anomaly. It is a massive, sprawling region with hundreds of thousands of times the mass of the Milky Way. Any explanation based solely on altering the laws of gravity must account for this enormous scale, including the motion of galaxies and the observed distortions of light. Beyond dark matter and modified gravity, other exotic physics scenarios are considered. Could there be a form of matter we have not yet discovered, one that interacts only gravitationally or weakly with normal matter? Could entire regions of space be filled with structures invisible to all current instruments, bending galaxies and light in ways we cannot yet detect? Some hypotheses stretch into the realm of the extraordinary, interactions with higher dimensions, fields that permeate space but are invisible, or relics of the early universe whose mass is concentrated in hidden clusters. These exotic ideas often emerge when standard models strain under the weight of observation. The Great Attractor is massive, complex, and hidden behind the dense plane of the Milky Way in the zone of avoidance. Its mass cannot be counted directly. Astronomers infer it from the motion of galaxies and the bending of light. If dark matter halos alone cannot account for every peculiarity in the velocity field, then new physics may be required. Physics that allows unseen mass or forces to shape the universe on scales far beyond what we can directly observe. The cinematic appeal of this scenario is undeniable. Galaxies stream toward a region of space shrouded in dust, their motion revealing something that cannot be seen. Light bends and twists as if painting the hidden mass on the canvas of the sky. The laws of physics, as we know them, strain to explain what we observe. Each measurement, each distortion, each peculiar motion is a clue pointing toward the unknown. The Great Attractor becomes not just a region of space, but a stage on which fundamental mysteries of matter, gravity, and motion play out. Dark matter remains the most plausible explanation, supported by gravitational lensing, galaxy rotation curves, and simulations of cosmic structure formation. Its presence allows astronomers to reconcile the enormous pull of the Great Attractor with the observable universe. The peculiar velocities of galaxies align with predictions from dark, matter-dominated models, and maps of cosmic flows trace its invisible scaffolding. Without it, The Great Attractor's gravitational influence is impossible to explain. Yet the very idea of dark matter invites deeper questions. What is it made of? Why does it interact only through gravity, refusing to shine or absorb light? How is it distributed on the scales of superclusters and cosmic filaments? The Great Attractor forces these questions into sharp relief. Its pull is so strong, its scale so vast, that it demands an explanation not just of mass, but of structure and distribution. The invisible web it hints at may stretch far beyond our local universe, influencing motion on scales that reach the limits of observation. Alternative theories, like modified gravity, challenge assumptions that have held for centuries. If the acceleration of gravity changes at low levels, then galaxies and clusters might move in ways that appear impossible without invoking dark matter. In this view, the Great Attractor is not an object or region filled with mass. It is a consequence of the laws themselves, bending differently across immense distances. The motion of the Milky Way, the peculiar velocities of surrounding clusters, the patterns in the flow field, these could all be manifestations of a universe governed by a more complex set of gravitational rules than previously imagined. Exotic physics scenarios extend the mystery further. Could higher dimensions exert a gravitational pull? Could dark energy or other unknown fields concentrate locally, creating anomalous motion? Could remnants from the early universe, relics of cosmic inflation, be lurking in the zone of avoidance, tugging on galaxies unseen? The possibilities are almost endless, limited only by imagination and the constraints of observation. Each theory carries implications not only for the Great Attractor, but for the fundamental understanding of matter, energy, and motion across the cosmos. The cinematic narrative is compelling. The Milky Way hurtles toward a hidden region, clusters of galaxies stream in coordinated flows, and light from the distant universe bends to reveal mass that cannot be touched or seen. Invisible forces shape the visible universe, exposing gaps in knowledge and suggesting realms of physics yet to be discovered. The Great Attractor is a laboratory for these ideas, providing a testing ground for dark matter models, modified gravity theories, and exotic physics hypotheses. Every new observation adds pieces to the puzzle, yet the full picture remains tantalizingly out of reach. Simulations of the universe under different physics assumptions reveal how extraordinary the Great Attractor truly is. Dark matter models reproduce the observed flows and lensing patterns, showing how massive halos can create the currents of motion we see. Modified gravity simulations struggle to match the complexity of observed flows on the scale of hundreds of millions of light years, yet they succeed in some local regions, hinting that a combination of factors might be at play. Exotic physics models remain speculative, but offer imaginative scenarios that could explain anomalies beyond the reach of conventional theories. The uncertainty and speculation are not signs of weakness, they are part of the excitement. The Great Attractor exists at the intersection of observation and theory, where visible light, gravitational effects, and cosmic flows converge to reveal something profoundly hidden. Dark matter, modified gravity, and exotic physics each offer pieces of the explanation, but the complete picture is still unfolding, awaiting more data, deeper analysis, and perhaps new ways of seeing the universe. Through it all, one fact stands out. The Great Attractor's influence is real. Galaxies move, light bends, and the universe responds to a gravitational pull far beyond what can be explained by stars and gas alone. Whether dark matter dominates, gravity behaves differently, or entirely new physics is at play, the result is the same. The universe is shaped by unseen forces, and our understanding is incomplete. This is where the narrative power comes from. The Great Attractor is a cosmic mystery with measurable consequences, a hidden mass whose presence is betrayed by the very motion of galaxies. It forces consideration of dark matter, tests the limits of gravitational theory, and opens the door to ideas that challenge everything we think we know about the universe. Its story is not written in light alone, but in motion, distortion, and the invisible scaffolding that binds the cosmos together. mass beyond sight? Could the universe be pulling on us? The universe we see is vast, but even the largest telescope only captures a fraction of it. Beyond the furthest galaxies we can observe, beyond the cosmic horizon, lies the unobservable universe, an expanse of space that light has not yet reached. And here is where one of the most unsettling possibilities arises. What if the motion of our Milky Way, the local group, and neighboring clusters is being influenced by mass that we cannot see at all? Not just hidden behind gas and dust, not merely dark matter in clusters, but mass that exists beyond the observable universe, entirely out of reach of our instruments. The idea sounds almost impossible. How can something we cannot detect, cannot measure, and cannot observe have a tangible effect on the motion of galaxies we can see? And yet, the evidence is there. The local group is not drifting randomly. It moves in a remarkably coherent way toward a direction that does not perfectly align with the nearest massive clusters, including the Great Attractor itself. There is a subtle mismatch between the expected motion based on known structures and the actual motion we measure. This mismatch suggests that the universe may extend its influence beyond the horizon, tugging at galaxies across cosmic distances. This line of thinking gave rise to the concept of dark flow. Unlike the Milky Way's ordinary motion, which is dominated by local gravitational sources, dark flow implies that entire regions of space, clusters, superclusters, perhaps even regions outside our observable patch, exert a gravitational pull on the local group. Galaxies, hundreds of millions of light years away, may be streaming in the same direction, as if following invisible currents that originate beyond the edge of the observable universe. The flow is subtle, detectable only through careful measurement of galaxy velocities and cosmic microwave background imprints. Yet it suggests forces far larger and stranger than anything seen locally. Observations of the cosmic microwave background, CMB, provide a critical window into this phenomenon. The CMB is the afterglow of the Big Bang, a uniform bath of radiation permeating the universe. Embedded within it are tiny temperature fluctuations, signatures of motion, and gravitational influences. When the Milky Way and local group move relative to this background, a dipole anisotropy appears, a slight warming in the direction of motion, a slight cooling in the opposite direction. Scientists have studied this dipole for decades, comparing it with velocities inferred from local clusters. The mismatch is telling. Known structures, including the Great Attractor and other nearby superclusters, cannot fully account for the observed motion. Something beyond, massive and unseen, might be tugging at us. The idea is controversial. In the early 2000s, teams using data from the Wilkinson Microwave Anisotropy Probe, WMAP, reported evidence of coherent motions of galaxy clusters inconsistent with local mass distributions. They called this effect dark flow, a term that immediately drew attention and debate. Some argued that the signal could be explained by statistical noise, foreground contamination, or biases in measurement techniques. Others saw it as the first hint that the universe's large-scale structure extends beyond the observable horizon, an astonishing notion that challenged standard cosmology. Scientific debates around this topic are fierce. One camp emphasizes the rigor of the measurements, highlighting cross-checks with independent surveys and the statistical significance of the velocity field anomalies. These proponents argue that the Milky Way, the local group, and surrounding clusters are moving coherently in ways that cannot be explained by visible mass alone. They suggest that dark matter halos beyond our observable horizon, or even gravitational effects from entirely unknown structures could be responsible. The implications are profound. Our observable universe may be only a fraction of the total cosmos, and unseen mass outside our horizon could already be shaping motion on enormous scales. Opposing voices are equally strong. Critics point out that dark flow signals are subtle, close to the limits of measurement precision. Systematic errors, foreground contamination, and the difficulties of measuring cluster velocities across vast distances all introduce uncertainties. Some papers argue that once corrections for these effects are applied, the evidence for dark flow largely disappears. Others note that standard cosmological models, including the lambda cold dark matter model, do not predict large-scale flows of the magnitude reported. The controversy is far from resolved, and each new dataset fuels further debate. Key papers illustrate the divide. In 2008, a team led by Alexander Kashlinsky analyzed X-ray cluster data from the Rosat satellite, combined with CMB maps, and concluded that galaxy clusters out to 1 billion light-years were moving coherently in a single direction with velocities of hundreds of kilometers per second. The interpretation? A gravitational pull from mass beyond the observable universe. The claim was sensational, suggesting forces from regions we cannot directly see are shaping the motion of galaxies we can. Others, including critics like F. Atrio Barandella and colleagues, examined the same datasets and questioned the methodology. They argued that subtle systematic biases in the CMB dipole extraction or in the modeling of cluster properties could create an apparent flow where none exists. Their analyses suggested that while some bulk motion is present, the evidence for a flow originating beyond the observable universe is not robust. The back and forth between these groups continued for years, highlighting the difficulty of interpreting subtle cosmic signals. Despite the controversy, the possibility remains tantalizing. If mass beyond our horizon can affect motion in our local group, then the universe is larger and stranger than we imagined. Structures billions of light-years away, unseen and unknowable in principle, could shape the paths of galaxies here and now. Gravity, the oldest and most familiar of forces, reaches across the limit of the observable universe, tugging on everything in its path. Our cosmic neighborhood becomes a small part of a larger network, responding to mass beyond our vision. This possibility intersects with other mysteries. The dark flow hypothesis suggests a connection between local gravitational anomalies, like the Great Attractor, and structures far beyond. Perhaps the Great Attractor is just the visible tip of a larger pattern, a local manifestation of a cosmic-scale flow extending across space. Its pull may be amplified or complemented by unseen mass lying outside the horizon, a reminder that motion is governed not just by what we can see, but by the unseen scaffolding of the universe. The debates also touch fundamental questions about cosmology. Standard models assume that the universe is homogeneous and isotropic on the largest scales. That matter is evenly distributed when averaged over enormous volumes. The existence of coherent flows driven by unseen mass could challenge this assumption, suggesting that the universe is more structured and lumpy than expected, even beyond the observable horizon. It forces scientists to consider whether our understanding of gravity, dark matter, or cosmic expansion needs revision. Controversy is the heartbeat of discovery. Every claim of motion from unseen mass sparks new observations, new simulations, and new interpretations. Telescopes scan the skies, mapping cluster velocities, refining redshifts, and measuring CMB dipoles with ever greater precision. Data is compared across instruments, from X-ray observatories to microwave satellites, from ground-based surveys to space telescopes. Each dataset either strengthens the case for mass beyond our horizon or forces a re-evaluation of earlier conclusions. The story is cinematic in scope. Imagine the Milky Way, carrying the local group, racing through space at hundreds of kilometers per second, influenced not only by known superclusters, but also by gravitational sources we cannot observe. Entire regions of the universe, stretching beyond the cosmic horizon, tug at us silently. Galaxies in every direction trace the flow, subtly nudged along invisible currents. The familiar stars overhead are part of a motion orchestrated by forces beyond sight, shaping paths and collisions on scales almost impossible to imagine. Scientific papers capture this drama. Some describe galaxy cluster motions with precise maps, plotting vectors across hundreds of millions of light-years. Others model the implications for cosmic structure formation, considering what unseen mass beyond the horizon would mean for the evolution of galaxies and clusters. The papers themselves read like detective stories. Evidence, counter-evidence, simulations and debates, all aimed at understanding motion that seems to originate from the unknowable, even within the standard cosmological framework. The possibility of mass outside the observable universe creates tension. Local gravitational anomalies like the Great Attractor can be modeled with dark matter, but explaining coherent flows on larger scales stretches models to their limits. Simulations of structure formation, based on observable mass and known dark matter distribution, sometimes fail to reproduce the magnitude of these flows, leaving room for speculation that unseen mass or unknown physics is at play. The idea that our local group could be influenced by mass beyond observation is unsettling and thrilling at the same time. It suggests a universe far grander than our telescopes can probe, a cosmic landscape where gravitational effects reach across unobservable realms. It implies that the Milky Way, Andromeda, and their companions are participating in a dance choreographed not only by nearby superclusters, but by forces originating in regions that lie forever beyond the horizon of light. These debates are ongoing. Papers continue to be published, methods refined, and new instruments launched. The Planck satellite, successors to WMAP, and future surveys aim to measure cosmic flows and the CMB dipole with unprecedented precision, potentially confirming or refuting the existence of dark flow. New simulations incorporate hypothetical mass beyond the observable universe to predict its effect on local galaxy motion. The controversies remain unresolved, yet every new result adds richness to the story, painting a universe in which the unknown can shape the known in profound ways. At its core, this issue is about limits. The observable universe is vast yet finite. Gravity, however, is not confined. Mass beyond sight can exert real influence, tugging at galaxies across billions of light-years. The Great Attractor may be only one actor in this drama, a visible manifestation of deeper forces stretching into the unseen universe. The local group's motion, the flow of clusters, and the distortions of cosmic background radiation may all carry the fingerprints of mass beyond our vision, shaping the cosmos in silence. This scenario, while speculative, is a reminder of the profound mysteries that remain. Our universe is not fully mapped. Unseen mass may lurk beyond, moving galaxies, bending light, and challenging our understanding of cosmology. The debates, the papers, the observations, all these are steps toward grasping forces that cannot be directly seen, yet leave measurable traces in the motion of everything around us. The Milky Way's motion in context. The Milky Way does not sit still. From the ground, from inside the disk, from the quiet illusion of a night sky that looks unchanged year after year, it feels stable. Stars rise, stars set, constellations return on schedule. Nothing suggests motion on a grand scale, but the calm is misleading. Our galaxy is moving through space at a speed so high that if it were happening on Earth, it would tear continents apart. And it is not moving randomly. It is moving with purpose, with direction, toward a region of space that does not announce itself with light. The Milky Way belongs to a small family of galaxies called the Local Group. This group includes Andromeda, Triangulum, and dozens of smaller galaxies, all bound together by gravity. Inside this group, galaxies orbit one another slowly, drawn together by mutual pull. But the Local Group itself is not isolated. It moves as a unit, drifting through the larger cosmic environment, responding to forces far beyond its own borders. The motion of the Milky Way is layered. At the smallest scale, the Sun orbits the galactic center. At a larger scale, the galaxy spins as a whole. At an even larger scale, the Milky Way and Andromeda move toward one another. And beyond all of that, the entire Local Group is being carried through space, pulled towards something massive enough to influence millions of light-years of territory. This larger motion was not discovered by watching stars drift across the sky. It was uncovered through subtle measurements, tiny shifts in light, patterns in cosmic radiation, and the collective behavior of galaxies far beyond our own. When astronomers traced these motions backward, they found that the Milky Way's path was not random. It aligned with a broad flow of galaxies, all heading toward the same general region of space. That region lies in the direction of the Great Attractor. From the Milky Way's point of view, this journey is invisible. The destination hides behind thick clouds of dust and gas in the plane of our own galaxy. The stars of the Milky Way block the view, creating a blind spot that astronomers call the zone of avoidance. Yet motion does not need sight to exist. Gravity reaches through darkness just as easily as it does through light. The Milky Way is moving at hundreds of kilometers per second relative to the cosmic background. That speed is not guessed, it is measured. The cosmic microwave background, the leftover radiation from the early universe, acts like a universal rest frame. When astronomers look at it, they see a slight temperature difference across the sky. One side is warmer, the other cooler. This dipole pattern reveals motion. It shows that our galaxy, along with its neighbors, is moving in a specific direction through space. When that direction is mapped onto the large-scale structure of the universe, it points toward the same hidden region where galaxy clusters, superclusters, and massive structures appear to concentrate. The Milky Way is not rushing toward a single object. It is being drawn into a massive gravitational basin, a region where matter, both visible and invisible, collects in overwhelming amounts. This motion places our galaxy within a vast river of cosmic flow. Galaxies around us are not scattered like leaves in the wind. They move along preferred paths, shaped by gravity over billions of years. These paths form the cosmic web, an enormous network of filaments and nodes where matter gathers. The Milky Way sits on one of these filaments, and that filament leads towards a dense region of space dominated by the Great Attractor. From this perspective, our galaxy's motion is not unusual. It is expected. Galaxies fall toward mass the way water flows downhill. What makes the situation extraordinary is the scale of the pull. The region influencing our motion is so massive that it overpowers local gravitational effects, guiding entire clusters of galaxies in the same direction. The Milky Way's journey is slow by human standards, but relentless by cosmic ones. In 1 million years, the galaxy will have moved far enough to change its position relative to distant background objects. In 1 billion years, its location within the cosmic web will be noticeably different. Over these immense timescales, the pull of the Great Attractor shapes not only where galaxies go, but how they evolve, collide, and merge. From a cosmic point of view, the Milky Way is a traveler caught in a current. This journey places our galaxy in context. We are not at the center of anything special. We are not stationary observers watching the universe expand from a fixed seat. We are participants in the motion. Our observations are made from a moving platform, one that is being drawn toward a massive structure we cannot fully see. This matters because motion changes perspective. The way we measure distances, velocities, and cosmic expansion depends on understanding how fast we are moving and in which direction. The Milky Way's motion toward the Great Attractor influences redshift measurements, velocity maps, and interpretations of large-scale structure. Without accounting for this motion, the universe would appear distorted, skewed by our own movement through space. The cosmic perspective strips away the illusion of stillness. The Milky Way is not an island floating peacefully in the void. It is part of a vast migration. Galaxies ahead of us are being approached. Galaxies behind us are being left behind. Entire regions of space are converging toward the same gravitational low point. This motion also reveals something deeper about how the universe organizes itself. On the largest scales, matter does not distribute evenly. It clumps, it gathers. Gravity amplifies tiny differences over time, pulling matter into denser and denser regions. The Great Attractor represents one of the most extreme outcomes of this process in our local universe. Its pull is strong enough to shape the motion of galaxies across hundreds of millions of light years. The Milky Way's trajectory shows how deeply embedded we are in this structure. Our galaxy's future path is tied to the same forces shaping distant clusters. The stars overhead, the spiral arms we live inside, the galactic center we orbit, all of it moves as part of a much larger pattern. From far away, if one could observe our region of space, the Milky Way would appear as a small luminous disk sliding along a filament of matter, drifting toward a crowded gravitational hub. Its motion would be subtle but clear, aligned with the flow of countless other galaxies, all responding to the same invisible pull. This perspective removes any sense of isolation. Our galaxy's journey toward the Great Attractor is shared by many others. Neighboring groups, distant clusters, and vast collections of galaxies all move together, tracing the contours of the same gravitational landscape. The universe is not a static backdrop. It is active, dynamic, shaped by forces that operate on scales far beyond direct experience. From within the Milky Way, the journey feels abstract. Nothing in daily life reflects it. Yet every observation we make of the universe carries the imprint of this motion. The direction we move affects the light we see, the temperatures we measure, the velocities we calculate. The Great Attractor is not just something out there. It is a force that shapes our frame of reference itself. The cosmic perspective reveals a simple truth. The Milky Way is not merely observing the universe. It is falling through it. The Lania supercluster. For most of modern astronomy, we had the wrong address. We knew the Milky Way lived in the local group, a small gathering of galaxies bound together by gravity. We knew this group sat near a larger collection called the Virgo cluster. And for decades, that was where the map stopped. Beyond Virgo, space felt vague, scattered, hard to organize. Galaxies appeared sprinkled across the sky without a clear sense of structure, like light seen through fog. The problem wasn't lack of data. It was perspective. Astronomers were measuring where galaxies were, how fast they were moving, how bright they looked. But those pieces weren't being assembled into a full picture of motion. Distance alone didn't tell the story. Position alone didn't explain behavior. What was missing was a way to see the universe not as a static snapshot, but as a flowing system, where galaxies move along invisible paths carved by gravity over billions of years. That shift changed everything. When scientists began focusing not just on where galaxies are, but on how they move relative to one another, patterns started to appear. These weren't small patterns or local ones. They were enormous, stretching across hundreds of millions of light years. Galaxies weren't just drifting away from each other due to cosmic expansion. They were streaming, sliding, and falling in coordinated directions, as if space itself had valleys and slopes. Those slopes pointed somewhere. By tracking the motion of tens of thousands of galaxies, astronomers realized our local group was part of a much larger structure, one defined not by borders you could see, but by gravity you could feel. This structure wasn't identified by a bright core or a neat shape. It was defined by motion, by the way galaxies flowed toward a common region of attraction. This was the birth of Lania. The name comes from Hawaiian, meaning immeasurable heaven or open skies, and it fits. Lania isn't a cluster in the traditional sense. It doesn't have a clear edge. It isn't round or symmetrical. It is a vast gravitational domain, a region of space where galaxies share the same overall motion, pulled toward the same deep gravitational basin. The Milky Way lives inside it. When astronomers mapped these galaxy flows in 3 dimensions, something remarkable happened. The paths of motion didn't scatter randomly. They converged. Like rivers feeding into a giant basin, galaxy velocities pointed inward, toward a central region that dominated the entire structure. That region aligned with what had long been called the Great Attractor. The Great Attractor wasn't just influencing nearby clusters anymore. It was acting as the anchor point for an entire supercluster-scale structure. Lania stretched across more than 500 million light-years and contained on the order of 100,000 galaxies, all moving within the same gravitational territory. This reframed our understanding of cosmic structure. Before Lania, Superclusters were identified mostly by where galaxies appeared dense: Virgo, Coma, Perseus, Pisces. These were names attached to visible concentrations. Lania wasn't visible in the same way. Its identity came from motion, not brightness. It was discovered by watching how galaxies behave, not how they look. The Great Attractor sat near the heart of this behavior. It wasn't a single object at the center of Lania, like a sun at the center of a solar system. It was more like the deepest part of a gravitational valley formed by overlapping concentrations of mass. Galaxy clusters, filaments, dark matter structures, all layered together, shaping the flow of everything around them. This explained something that had puzzled astronomers for decades. Galaxies near us weren't just moving away due to cosmic expansion. They had extra motion layered on top, a shared drift toward a hidden direction. That drift wasn't random noise, it was organized, it had structure. And that structure defined Lania's boundaries. Inside Lania, galaxies fall inward. Outside it, galaxies flow toward different attractors, different basins, different gravitational lows. The universe isn't divided by lines or walls. It's divided by gravity's reach. The discovery of Lania turned the Great Attractor from a strange anomaly into a central player. Instead of being an isolated mystery, it became part of a larger system. Its pull helped define the shape and behavior of our entire cosmic neighborhood. The Milky Way wasn't just moving towards something strange. It was participating in a massive, coherent flow, shared by countless other galaxies. This also changed how astronomers thought about where we are. We are not simply near Virgo. We are not just members of the local group. We are residents of a supercluster-sized gravitational domain, one that extends far beyond what the eye can see and deep into regions hidden behind our own galaxy's dust. The zone of avoidance still blocks direct views of large portions of Lania's core, but motion does not hide behind dust. Velocities cut through obscuration. Even when galaxies cannot be seen clearly, their influence shows up in the way others move. That's how Lania was drawn, not as a static map, but as a dynamic one. Arrows instead of dots, paths instead of points. The Great Attractor sat at the convergence of those arrows, a silent organizer of motion on a colossal scale. What makes this unsettling is how late we discovered it. For centuries, humans believed the Milky Way was the universe. Then we learned it was one galaxy among many. Then we learned those galaxies formed clusters, then superclusters. And only recently did we realize that even superclusters are not isolated islands, but parts of larger gravitational territories defined by flow. Each step pulled us farther from the idea of a simple, neatly arranged cosmos. Lania showed that the universe is shaped less like a collection of objects and more like a landscape, with slopes, basins, and currents. The Great Attractor is one of the deepest basins in our region, powerful enough to guide the motion of galaxies across distances so large that light itself takes hundreds of millions of years to cross them. From within the Milky Way, this landscape is impossible to see directly, but its influence is everywhere. It's written into the velocities of galaxies, into the direction of our motion relative to the cosmic background, into the way large-scale structures align across the sky. Lania is not our destination. Galaxies do not crash into its center all at once. The journey is slow, stretched across cosmic time, but the pull is constant. The Great Attractor does not announce itself. It does not flare or shine. It simply bends the paths of everything nearby, quietly shaping the architecture of our local universe. And for the first time, we know its neighborhood has a name. Why this matters for physics, cosmology, and our place in the universe. At first glance, the Great Attractor and the vast structures tied to it feel distant, abstract, removed from everyday life. They sit hundreds of millions of light years away, hidden behind dust, invisible to the eye. But their importance is not remote. It reaches directly into how humans understand reality, how science tests its own rules, and how confident we can be about the picture of the universe we've built. This phenomenon forces scientists to confront a simple but uncomfortable idea. Our understanding of the universe is incomplete in measurable, testable ways. For decades, physics and cosmology have relied on models that work extremely well in most situations. Gravity predicts planetary motion. General relativity explains how light bends and how space curves. The standard model of cosmology describes how the universe expands and how matter clumps over time. These frameworks are powerful, precise, and supported by massive amounts of data. But the Great Attractor does not fit neatly inside them. The issue isn't that the math breaks outright. It's that the observations demand more mass, more structure, more influence than what the visible universe alone can provide. When astronomers track galaxy motion on these enormous scales, the numbers refuse to balance. Something is pulling harder than expected. Something is shaping motion beyond what current maps of matter predict. That gap matters deeply. Physics advances not when theories work, but when they fail in specific, repeatable ways. The Great Attractor is one of those failures. It doesn't overthrow known laws, but it exposes their limits. It highlights where assumptions break down and where hidden factors must exist. This is how progress starts. Understanding this phenomenon directly impacts how gravity is treated on the largest scales. Gravity behaves differently when spread across hundreds of millions of light years than it does inside a solar system. Tiny deviations, insignificant locally, become dominant when amplified across cosmic distances. The Great Attractor gives scientists a real-world laboratory to test whether gravity behaves exactly as expected when pushed to extremes. This isn't philosophical, it's mechanical. It's about numbers lining up or not lining up. If gravity alone cannot explain the observed flows, then either unseen mass exists in vast quantities, or gravity itself behaves differently on these scales. Each possibility leads to radically different futures for physics. One path deepens the role of dark matter. The other opens the door to changes in how gravity is described. For cosmology, the stakes are just as high. Modern cosmology depends on the idea that on very large scales, the universe is roughly uniform. Structures exist, but they average out. The Great Attractor challenges how clean that averaging really is. Its influence stretches across regions large enough to blur the line between local motion and universal behavior. When astronomers measure expansion, they must subtract local motion. But where does local end when structures this large exist? The Great Attractor forces cosmologists to refine how they separate universal expansion from regional gravitational pull. Without doing that correctly, measurements of cosmic parameters shift subtly, but meaningfully. Small errors compound. This affects estimates of the universe's age, its expansion rate, and its future behavior. The Great Attractor is not just a curiosity, it's a calibration problem for the entire field. Ignoring it leads to distorted interpretations. Accounting for it improves precision across cosmology. There's also a deeper consequence tied to how humans map reality. For most of history, humans placed themselves at the center of everything. First Earth, then the Sun, then the galaxy. Each discovery pushed us outward. The Great Attractor continues that trend, not by moving us physically, but by relocating our sense of cosmic position. We don't live in a random patch of space. We live in a gravitational watershed. That idea changes how scientists think about cosmic environment. Galaxies don't evolve in isolation. Their paths, interactions, and growth depend on where they sit within large-scale flows. The Milky Way's history is shaped by the gravitational currents it travels through. Its future collisions, mergers, and structure are influenced by this environment. Understanding the Great Attractor helps explain why our galaxy exists in its current form. This knowledge feeds directly into simulations of galaxy formation. When scientists model how galaxies grow over billions of years, they must place them inside realistic environments. A galaxy falling through a massive gravitational basin evolves differently than one drifting in a quieter region of space. Star formation, gas inflow, and interaction rates all change. Human understanding of galactic history improves by acknowledging these forces. There's also a technological significance. Studying phenomena like the Great Attractor pushes observational tools to their limits. It demands better surveys, deeper sky coverage, higher precision measurements. The effort to understand it drives innovation in data analysis, telescope design, and computational modeling. These advances don't stay confined to cosmology. They spill into other sciences, from climate modeling to medical imaging, wherever large datasets and complex simulations are used. Big cosmic problems create practical solutions. On a more fundamental level, this phenomenon sharpens scientific humility. The Great Attractor was influencing our galaxy long before humans existed. It shaped cosmic motion while civilizations rose and fell, while species evolved, while planets formed. And yet, we only noticed it recently, not because it suddenly appeared, but because our tools were finally sensitive enough to reveal it. That delay is instructive. The universe can hide enormous structures in plain sight. That absence of evidence is not evidence of absence. That confidence must always remain provisional. The Great Attractor teaches caution in claims of completeness. No matter how elegant a theory appears, nature may still be holding something back. This matters for how humans approach science. There's also a cultural impact, even if subtle. Discoveries like this reshape how humanity tells its story, not in a poetic sense, but in a factual one. Our place in the universe is not static. It's dynamic, shaped by forces beyond perception. We are moving through a landscape shaped by invisible mass, governed by laws still being tested. That knowledge does not diminish humanity. It sharpens it. It shows that intelligence can detect the unseen, measure the invisible, and reconstruct massive structures using nothing but light, motion, and patience. The Great Attractor is not something humans can visit, touch, or photograph directly. Yet its presence is undeniable, mapped through reasoning and evidence alone. That achievement matters. It demonstrates the power of scientific thinking at its best. No guesswork, no authority, just observation, measurement, and relentless questioning. The Great Attractor stands as proof that even the most hidden forces leave traces, and that humans are capable of following those traces across unimaginable distances. Understanding this phenomenon also prepares science for future discoveries. If structures this massive can remain partially hidden behind our own galaxy, what else exists beyond current detection limits? What other flows, attractors, or anomalies shape regions we haven't mapped yet? The Great Attractor becomes a reference point, a warning sign that the cosmic inventory is not finished. Future observations. For a long time, the Great Attractor lived in a strange space between certainty and blindness. Astronomers could feel it through motion, calculate it through numbers, watch galaxies drift toward it as if sliding downhill, yet still struggle to actually see what was doing the pulling. It wasn't that the universe refused to reveal it, but that human tools simply weren't built for this kind of target. Massive, spread out, buried behind dust, and operating across hundreds of millions of light years, the Great Attractor demanded a new way of observing the sky, not sharper eyesight alone, but better reach across wavelengths, time, and scale. That shift is happening now. The next generation of observatories is not arriving with the promise of a single dramatic image or a clean reveal. Instead, they are arriving with something far more powerful. The ability to fill in missing pieces that have shaped every discussion about the Great Attractor so far. These tools are designed to work where older ones struggled, to see through what once blocked us, and to trace motion and structure with a level of detail that turns guesswork into mapping. The James Webb Space Telescope sits at the center of this change, not because it was built to hunt the Great Attractor directly, but because it changes how astronomers look into the most obscured parts of the universe. Webb sees in infrared light, which moves through dust the way visible light cannot, slipping past thick star fields and gas clouds that once turned large regions of the sky into blank spots. In directions close to the plane of the Milky Way, where the Great Attractor hides behind layers of cosmic clutter, Webb's vision is like lifting a heavy curtain that has blocked the view for decades. What Webb brings to the table is not spectacle but clarity. It allows astronomers to spot galaxies that were always there but effectively invisible. buried behind our own galaxy's glow. Each newly detected galaxy adds weight to the map, not metaphorically, but literally, because gravity cares about mass whether it shines brightly or barely at all. With Webb, scientists can finally count more of the matter that contributes to the gravitational pull shaping galaxy motion in this region of space. Beyond detection, Webb can examine these galaxies in detail, breaking down how their stars are arranged, how gas moves inside them, and how their shapes compare to galaxies in quieter regions of the universe. Subtle differences matter here. Galaxies that have spent billions of years falling through a strong gravitational environment often carry signs of that journey in their structure, in how tightly stars are packed, in how gas flows inward or gets stripped away. These details help astronomers understand not just where mass is, but how it behaves under sustained gravitational influence. While Webb works deep and narrow, the Vera Rubin Observatory approaches the sky in the opposite way, sweeping wide and returning again and again to the same regions, building a living record of the universe in motion. Rubin is not focused on single targets. It is designed to watch everything it can, repeatedly, patiently, with consistency that earlier surveys could never maintain. This constant return is what makes it powerful, because it turns snapshots into stories. For studies tied to the Great Attractor, Rubin's strength lies in precision through repetition. Measuring galaxy motion is difficult, not because the effect is small, but because uncertainty creeps in from every direction. Distance estimates wobble, velocities carry noise, individual errors blur the picture. Rubin attacks that problem by sheer volume and consistency, observing millions upon millions of galaxies with the same system, the same calibration, the same sky coverage over many years. As this dataset grows, patterns that once looked rough begin to sharpen. Flow maps become cleaner, velocity fields smooth out. Structures that once appeared broken or fragmented start to connect. Rubin doesn't just improve existing maps, it changes how confident scientists can be in them, turning debated features into measurable ones and narrowing the range of possible explanations. Rubin also plays a key role in refining distances, which is crucial because motion without accurate distance is just noise. By tracking subtle brightness changes and using large statistical samples, astronomers can tighten distance estimates across huge volumes of space. When distance improves, velocity measurements fall into place, and when velocity measurements improve, gravitational models stop wobbling. Radio astronomy adds another critical layer, one that operates almost completely independent of the visual universe humans are used to imagining. Next-generation radio arrays are built to listen for faint signals from hydrogen gas spread across intergalactic space, signals that pass through dust as if it weren't there. Where optical surveys see clutter, radio surveys see structure. Hydrogen mapping is especially important because hydrogen outlines the large-scale framework of matter. It fills filaments, traces the paths galaxies follow, and highlights regions where gravity has gathered material long before stars fully formed. By mapping hydrogen near the Great Attractor's direction, astronomers can trace the scaffolding of mass that guides motion, revealing whether matter is smoothly distributed or concentrated into deeper gravitational pockets. Radio measurements also offer a separate way to track motion, using shifts in frequency that reflect how gas clouds move through space. This provides an independent check on velocity data gathered from optical and infrared surveys. When different methods point to the same flow patterns, confidence rises. When they disagree, scientists know exactly where to dig deeper. X-ray observations complete the picture by revealing where gravity has heated gas to extreme temperatures. Massive structures trap gas so effectively that it heats up and glows in X-rays, turning invisible mass into detectable energy. If large amounts of hot gas exist near the heart of the Great Attractor's influence, X-ray surveys can map its extent and shape, showing how deep and wide the gravitational well really is. What makes this era different from earlier attempts is coordination. These observatories are not working in isolation. Their data feeds into shared models, layered on top of one another, filling gaps left by other wavelengths. Infrared reveals hidden galaxies. Optical surveys map structure across time. Radio traces gas and motion through dust. X-rays highlight deep gravitational wells. Together, they transform a once shadowy region into a richly described environment. As observations improve, simulations evolve alongside them. Modern simulations are no longer simple approximations. They track billions of particles, modeling how matter flows under gravity across cosmic time. With better observational input, these simulations become stricter tests rather than loose illustrations. Scientists can ask whether structures like the Great Attractor naturally emerge under known physics, or whether something extra must be added to match reality. Future observations will not deliver a single moment of revelation. There will be no dramatic unveiling where the Great Attractor suddenly appears in full view. Instead, understanding will deepen gradually as uncertainty shrinks and models tighten, as hidden mass becomes less hidden, and as galaxy motion aligns more cleanly with mapped structure. The story moving forward is one of refinement, not surprise, where better tools slowly replace mystery with detail, turning a gravitational force once inferred only through motion into a well-characterized feature of our cosmic neighborhood, shaped not by imagination, but by relentless measurement across every wavelength the universe offers. What scientists hope to learn. For decades, one of the most frustrating parts of studying the Great Attractor has been that the most important region sits directly behind our own galaxy, hidden not by distance, but by clutter. The Milky Way, beautiful as it is from the inside, becomes a wall when viewed from Earth, its dense lanes of dust and billions of stars flooding the sky and drowning out the faint light coming from far beyond. This blocked region, known as the zone of avoidance, has shaped every conversation about the Great Attractor, not because it holds all the answers, but because it has kept so many of them just out of reach. What scientists hope to learn first and foremost is what is actually there. Not guesses, not indirect hints, not rough reconstructions built from motion alone, but a detailed, layered map of the galaxies, gas and structures hiding behind the Milky Way's glare. The zone of avoidance has never been truly empty. It only appeared that way because older instruments could not separate distant galaxies from the foreground noise of our own. As observational tools improve, that illusion is slowly breaking down, revealing that this region is crowded, structured, and deeply important to understanding why galaxies move the way they do. Precise mapping of the zone of avoidance means turning a blind spot into a readable landscape. It means identifying individual galaxies that were once lost in the background, measuring their distances accurately, tracking how they cluster together, and following how their motion fits into the larger flow toward the Great Attractor. Each new detection fills a gap that once forced astronomers to make assumptions, and fewer assumptions mean stronger conclusions. This mapping is not about creating a prettier picture of the sky. It's about resolving uncertainties that have echoed through cosmology for years. When scientists model gravitational pull, missing mass skews the results. When entire regions are undercounted, flow models bend unnaturally to compensate. A clearer view of the zone of avoidance allows gravity to be calculated honestly, based on what is actually there rather than what is guessed to be missing. As the fog lifts, scientists expect to learn whether the Great Attractor's pull comes from a broad spread of mass or from tighter concentrations hidden in this region. They want to know if the gravitational influence is dominated by massive clusters packed closely together, or by long filaments of matter feeding into a deeper core. That distinction matters because it changes how gravity operates across large distances and how galaxies respond to it over billions of years. Mapping also reveals connections. Structures do not exist in isolation. Galaxies form chains, filaments, walls, and knots that guide motion like channels guide water. By tracing these structures through the zone of avoidance, astronomers can see how matter flows into the Great Attractor's region, identifying the pathways along which galaxies travel and the larger framework that organizes the local universe. Alongside this effort sits an even larger question, one that reaches beyond visible matter entirely and moves straight into the heart of modern cosmology. how dark matter is distributed in this region. Dark matter does not shine, it does not glow, it does not emit light at any wavelength, and yet it outweighs visible matter by a wide margin and dominates gravity on large scales. The Great Attractor is one of the strongest hints that dark matter is not spread evenly, but gathered into massive concentrations that shape the universe quietly and relentlessly. Scientists hope to learn not just that dark matter is present near the Great Attractor, but how it is arranged. Is it smoothly spread across large volumes, creating a gentle but wide-reaching pull? Or is it clumped into dense halos surrounding galaxy clusters, creating sharper gradients in gravity? The answer affects everything from galaxy motion to the growth of cosmic structure itself. Understanding dark matter distribution requires combining multiple lines of evidence. Galaxy velocities show where gravity is strongest. Gravitational lensing reveals how mass bends light even when that mass cannot be seen directly. Gas motion traces invisible scaffolding. When these methods point to the same regions, a picture begins to form not of individual objects, but of an underlying mass landscape that governs motion on colossal scales. In the case of the Great Attractor, scientists are especially interested in whether dark matter accounts fully for the observed pull, or whether discrepancies remain even after it is included. If dark matter explains the motion cleanly, it strengthens current models and helps pin down how much dark matter exists and how it behaves. If it does not, then something deeper is at play. That possibility leads directly into the third goal driving future study: testing new physics theories. The Great Attractor occupies a regime where gravity operates over distances so large that even small deviations from known laws would become noticeable. This makes it an ideal testing ground. Not because scientists expect gravity to suddenly fail, but because this is where subtle effects would show themselves first, magnified by scale. Some alternative gravity models predict slightly different behavior in regions with low acceleration or large distances between masses. These differences are too small to detect in solar systems or even galaxy clusters, but across supercluster-sized regions, they could shape motion in measurable ways. By comparing predicted flows with observed ones near the Great Attractor, scientists can test whether standard gravity holds up or whether adjustments are needed. This testing is slow and careful, grounded in data rather than speculation. Models must match not just one observation, but many, across different scales and directions. The Great Attractor's complexity makes it a difficult target, but also a valuable one, because simple explanations struggle there. If a theory works in this environment, it gains credibility. If it fails, it reveals exactly where its limits lie. Scientists are also interested in whether the Great Attractor hints at influences beyond the observable universe. Large-scale flows that appear unusually aligned or stronger than expected raise questions about mass distributions outside the regions we can see. While this idea remains debated, mapping motion with greater precision allows scientists to test whether such explanations are necessary or whether known structures are sufficient once fully accounted for. What ties all of this together is the desire to replace inference with clarity. For years, the Great Attractor has been defined by its effects rather than its form. Galaxies move, so something must be pulling them. Velocities align, so a structure must exist. Future observations aim to turn those effects into detailed maps, revealing not just that something is there, but what shape it takes, how it formed, and how it fits into the broader architecture of the universe. This pursuit matters because it sharpens every other measurement in cosmology. When scientists understand local gravitational environments better, they can subtract their influence more accurately from universal measurements. Expansion rates become cleaner, flow models become more reliable, simulations align more closely with reality. Maps of large-scale structure. For most of human history, maps were about surfaces, coastlines, mountains, rivers, borders. Even when astronomy began mapping the sky, it followed the same instinct, turning stars into dots, constellations into shapes, galaxies into catalogues arranged by brightness and position. These early cosmic maps were useful, but they missed the most important thing about the universe, which is that it is not arranged like a scatter of objects pinned onto a flat background. It is shaped by motion, by gravity, and by connections that only appear when distance, direction, and velocity are combined into a single picture. Large-scale structure maps are where that realization finally comes into focus. Instead of asking where galaxies are, these maps ask how galaxies relate to one another across enormous distances, how they cluster, how they align, how they move, and how all of that motion traces invisible scaffolding, made mostly of mass that cannot be seen. These maps don't look like traditional star charts. They look like tangled webs, sprawling networks of filaments, knots, and empty voids, stretching across hundreds of millions of light years. The Great Attractor sits inside this web, not as a neat point on a grid, but as a region where many threads converge. What scientists want from improved maps of large-scale structure is resolution, not sharpness in the photographic sense, but clarity in how mass is arranged across space. Earlier maps were coarse. They showed general trends, but blurred the details. They could tell that galaxies were clustering, but not exactly how those clusters connected, or where their gravitational influence began and ended. As data improved, the universe began to look less like a random spread and more like a living system. Galaxies traced long, thin filaments. Those filaments fed into dense nodes. Between them stretched vast voids, regions where matter was scarce and gravity weak. Motion followed structure. Galaxies flowed along these filaments the way water follows channels carved into land. Mapping this structure precisely is essential because gravity follows mass, not light. If the map is wrong, the physics built on top of it will be wrong too. Large-scale structure maps are built by stacking multiple layers of information. Distance measurements place galaxies in 3 dimensions. Velocity data adds direction and speed. Density estimates reveal where matter piles up. When these layers are combined, a dynamic map emerges, one that shows not just where galaxies sit now, but where they are headed and what forces guide them. For the Great Attractor, this kind of mapping is critical because its influence is not confined to a small region. It shapes motion across a broad swath of space, meaning that its true form can only be understood by seeing how surrounding structures feed into it. Scientists are looking for continuity, for filaments that stretch from distant regions and funnel matter inward, revealing whether the Great Attractor is the deepest part of a single massive basin or one node within an even larger network. As maps improve, boundaries become clearer. In large-scale structure mapping, boundaries are not drawn with lines. They are defined by flow. A galaxy belongs to a structure not because it sits near others, but because it moves with them, because it shares the same gravitational destination. Improved maps allow scientists to trace these flow boundaries with greater confidence, separating one gravitational domain from another without guessing where one ends and the next begins. This matters because earlier models often treated large structures as isolated or loosely connected. Better maps reveal that many of these structures overlap, merge, and influence one another in complex ways. The universe is not built from clean blocks. It is layered, with structures embedded inside larger ones, each shaping motion at its own scale. As observational coverage expands, scientists can test whether current maps underestimate or overestimate the reach of major attractors. Small shifts in mapping can have large effects on interpretation. A filament placed slightly wrong can redirect inferred motion. A missing cluster can flatten a gravitational gradient that should be steep. Precision here is not cosmetic. It determines whether models match reality or drift away from it. Another goal of large-scale structure mapping is consistency. Different surveys have historically produced slightly different pictures, not because the universe changes, but because instruments, methods, and coverage vary. New mapping efforts aim to unify these views, stitching together data from different wavelengths and techniques into a single coherent framework. When maps agree across methods, confidence grows. When they don't, scientists know exactly where the uncertainties live. These improved maps also allow time to enter the picture. While galaxies move slowly on human timescales, their collective motion leaves patterns that reflect billions of years of evolution. Large-scale maps let scientists rewind the cosmic clock, testing whether observed structures could have formed under known conditions or whether something extra must have shaped them. If the Great Attractor sits where simulations predict, that supports existing models. If it doesn't, the discrepancy becomes a clue rather than a problem. There is also a practical side to these maps that often goes unnoticed. Large-scale structure maps act as correction tools for nearly every major measurement in cosmology. When scientists measure expansion, background radiation, or galaxy distributions, they must account for local structure to avoid bias. A more accurate map means cleaner data across the board, reducing uncertainty in results that depend on subtracting local gravitational effects. As maps grow more detailed, they also reveal how rare or common structures like the Great Attractor really are. Is it an extreme example of something that exists everywhere, or is it unusual even by cosmic standards? Answering that question depends entirely on having a large enough sample mapped with enough precision to compare similar regions fairly. What emerges from this effort is not a static atlas, but a dynamic framework, one that treats the universe as a system in motion rather than a frozen snapshot. Galaxies stop being isolated objects and become markers tracing invisible forces. Space itself stops looking empty and starts looking structured, shaped by gravity in ways that only reveal themselves when scale and motion are taken seriously. Large-scale structure maps are where the Great Attractor finally stops being just a mystery inferred from movement and becomes part of a visible, measurable landscape. A landscape where mass, motion, and structure line up in a way that allows scientists to ask sharper questions and demand clearer answers. How these maps are reshaping models of cosmic flow. For a long time, cosmic motion was treated as a background detail, something assumed to be smooth, slow, and predictable once the expansion of the universe was taken into account. Galaxies were expected to drift apart neatly, with only small local movements caused by nearby mass. That picture worked on paper, but once large-scale structure maps became detailed enough, it began to fall apart in ways that were impossible to ignore. These maps showed that galaxies do not simply ride the expansion of space, like leaves floating down a calm river. Instead, entire regions of the universe move together in coordinated streams, bending, accelerating, and merging as if guided by invisible terrain. The moment scientists began plotting these flows in 3 dimensions, the idea of a quiet, evenly expanding universe stopped matching what the data showed. Cosmic flow maps do not just record where galaxies are. They reveal where galaxies are going, how fast they are moving, and how their motion compares to the expansion expected from cosmic distance alone. This difference between expected motion and actual motion is where everything starts to change. When mapped across tens and hundreds of millions of light years, these differences form large, coherent patterns that no simple model predicted. Instead of random deviations, the maps showed highways of motion. Galaxies far apart from one another were drifting in the same direction at similar speeds, even when visible matter between them was sparse. These flows curved toward massive regions that were not obvious in optical surveys, bending paths across space in a way that felt less like chance and more like structure. Once these flows were laid over density maps, something striking appeared. The motion of galaxies traced the same hidden framework as the cosmic web itself. Dense regions pulled matter inward along long filaments, while vast voids pushed matter outward, not through force, but through imbalance. Gravity was not acting locally. It was shaping motion across immense scales. Traditional models struggled here because they treated gravity as a series of local pulls stacked together. Large-scale structure maps showed that this approach missed the bigger picture. Motion was not being dictated by individual galaxy clusters acting alone. It was being guided by the overall shape of mass distribution across entire regions of the universe. This forced a shift in how cosmic flow was modeled. Instead of starting with visible mass and calculating motion outward, scientists began working backward. They used observed galaxy velocities to infer where mass had to be, even when it could not be seen directly. Flow maps became a kind of reverse blueprint, allowing astronomers to sketch the gravitational landscape first and fill in the matter later. As these reconstructions improved, it became clear that some flows were too strong, too organized, and too extensive to be explained by known structures alone. Entire clusters were drifting together toward the same general region, not just neighboring systems, but vast collections of galaxies spanning hundreds of millions of light-years. This motion was not subtle. It was fast, persistent, and directional. The idea of cosmic flow shifted from a minor correction to expansion models into a central feature of how the universe behaves on large scales. Expansion was no longer the only driver. The universe was expanding, yes, but it was also streaming, funneling matter along paths shaped by deep gravitational wells that spanned enormous volumes of space. Large-scale structure maps showed that these flows do not stop at the edges of galaxy clusters. They extend across superclusters, linking distant systems into shared motion. From a local perspective, a galaxy might appear isolated, but in the map, it is part of a river of matter stretching far beyond what any telescope image alone could suggest. This redefined what scientists meant by local motion. A galaxy's movement could no longer be explained only by its immediate surroundings. Its velocity carried the signature of mass far beyond its visible neighborhood. Motion became a record of long-range gravitational influence, written into the speed and direction of galaxies themselves. As flow maps grew more detailed, they revealed boundaries that were never visible before. These boundaries were not walls or edges, but transition zones where motion shifted direction. On one side, galaxies drifted toward one gravitational basin. On the other, they flowed toward a different one. These invisible borders carved the universe into regions defined not by appearance, but by motion. This concept changed how cosmic regions were defined. Instead of grouping galaxies based on proximity or brightness, scientists began grouping them based on shared flow patterns. If galaxies moved together over vast distances, they belonged to the same dynamical region, even if they were spread across huge volumes of space. The maps showed that cosmic flow behaves more like weather than clockwork. Streams merge, split, slow down, and accelerate depending on the underlying mass distribution. Some flows are smooth and steady, others twist and curve as they pass through complex gravitational terrain. This behavior does not fit neatly into older, simplified models. What made this especially disruptive was that the strongest flows pointed toward regions that were difficult to observe directly. Optical surveys often showed little there, yet the flow maps insisted that something massive was shaping motion in those directions. The mismatch between visible matter and inferred gravitational influence became impossible to dismiss. As a result, models of cosmic flow had to incorporate unseen mass more aggressively. Instead of treating dark matter as a background component, it became the main architect of motion. Flow maps did not merely support its existence, they required it. Without a dominant invisible mass component, the observed patterns simply could not form. These maps also revealed that voids play a larger role than previously thought. Regions with very little matter act like gravitational low-pressure zones. Galaxies are not pulled out of voids by force. They drift away because there is more mass elsewhere. Flow maps show this clearly, with streams bending around empty regions as if avoiding them. This insight reshaped how scientists model large-scale motion. Instead of focusing only on attractors, they began modeling repellers as well, regions where the absence of mass pushes matter outward. Cosmic flow became a balance of pulls and escapes, guided by both what exists and what does not. Another shift came from time. Flow maps are not static snapshots. They encode history. The current motion of galaxies reflects billions of years of gravitational influence. When scientists simulate these flows backward, they can reconstruct earlier states of large-scale structure, revealing how today's cosmic web grew into its current form. This backward modeling showed that some flows have remained stable for immense periods, while others evolved as structures grew and merged. The persistence of certain flow patterns suggested that the underlying mass structures responsible for them are deeply rooted in the universe's early history. As more data was added, the maps grew smoother, not noisier. Random motion faded into the background, while large coherent flows stood out more clearly. This was a critical point. If the patterns were artifacts or errors, they would blur with more data. Instead, they sharpened. The reshaping of cosmic flow models did not happen quietly. It forced revisions in simulations, altered assumptions about structure formation, and raised questions about whether current models fully account for the largest gravitational influences at play. Flow maps stopped being diagnostic tools and became central constraints that any successful model had to match. What these maps ultimately showed was that motion is one of the most honest signals the universe provides. Light can be blocked, distorted, or hidden, but motion carries the imprint of mass, no matter how well it is concealed. By following the paths galaxies take through space, scientists uncovered a universe that is far more connected, directional, and structured than early models ever suggested. And as these maps continue to grow in scale and resolution, they are no longer just reshaping how cosmic flow is understood. They are quietly rewriting how the universe itself is divided, defined, and navigated by the matter inside it. How voids and filaments influence motion near massive attractors. Cosmic motion does not happen in empty uniform space. Galaxies move through a universe shaped like a vast, uneven landscape, carved by dense filaments of matter and stretched open by enormous voids. When large-scale maps became detailed enough to show this structure clearly, it stopped making sense to think of motion as something driven only by big attractors pulling from afar. The empty regions mattered just as much, sometimes more, and the filaments connecting everything turned out to be the main roads along which motion actually happens. Voids look calm on images, but they are anything but passive. These regions contain very little matter compared to the cosmic average, and that imbalance creates motion without any direct pulling force. Galaxies near voids drift away from them simply because gravity is stronger elsewhere. The effect builds slowly but relentlessly over billions of years, pushing matter toward denser regions and feeding the growth of filaments and attractors. When motion near massive attractors is mapped carefully, voids show up as invisible pushers in the background. Galaxies do not fall straight inward from all directions. Their paths curve, slide, and bend, shaped by nearby emptiness as much as by distant mass. A galaxy sitting between a large void and a dense filament does not hesitate. It moves away from the void and into the filament, not because it is being yanked, but because the gravitational field is uneven. Filaments are where this redirected motion becomes organized. These long, rope-like structures connect clusters across enormous distances, guiding galaxies along narrow paths. Motion inside filaments looks nothing like random drift. Galaxies flow along them in streams, sometimes accelerating, sometimes slowing, depending on how mass is distributed ahead of them. Near massive attractors, these filaments act like funnels, feeding matter inward from far beyond the attractor's visible edge. Flow maps show that galaxies rarely approach major attractors directly through open space. Instead, they arrive through filaments, already aligned and moving in coordinated streams long before they reach the densest regions. This changes how attraction is understood. The pull does not act on isolated galaxies scattered across space. It acts on entire channels of matter already moving together. Voids amplify this effect by sharpening the contrast. On one side, gravity is weak because little mass exists. On the other side, filaments grow denser as they absorb matter drifting away from emptiness. This contrast creates preferred directions of motion. Galaxies near massive attractors often follow curved paths that trace the filament network rather than heading straight inward. Near the most powerful attractors, multiple filaments converge. Each one brings its own stream of galaxies, shaped by different voids and density patterns farther out. Motion becomes layered. Some galaxies approach quickly along thick filaments, others drift in more slowly through thinner ones, and very few arrive from directions dominated by large voids. This layered motion explains why velocity maps near massive attractors look complex instead of chaotic. The motion is structured, not noisy. Galaxies with similar speeds and directions often share the same filament, even when they are spread across huge distances. Their shared motion is not coincidence. It is inheritance from the gravitational terrain they travel through. Voids also influence speed. Galaxies pushed out of large empty regions gain momentum gradually over long distances. By the time they reach filament intersections near attractors, they are already moving fast. This pre-acceleration matters. It means massive attractors do not need to account for the full observed velocities on their own. Part of the motion is handed to them by the voids upstream. This realization changed how scientists interpret high-speed galaxy flows near major attractors. Earlier models often assumed that fast motion meant extreme local mass. Flow maps showed a different picture. The speed could reflect a long journey shaped by voids and filaments, not just the pull of the destination. Filaments also act as stabilizers. Motion inside them stays coherent over vast distances, resisting random scattering. This coherence explains why large groups of galaxies move together toward the same region without breaking apart. The filament provides structure, direction, and gravitational guidance long before the galaxies feel the strongest pull of the attractor itself. Near massive attractors hidden behind dense regions of the sky, this filament-driven motion becomes especially important. Even when direct observation is limited, the direction and shape of incoming flows reveal where the filaments must be. Motion traces structure, even when light cannot. Void boundaries show up clearly in flow maps as sharp changes in direction. Galaxies near these boundaries behave differently depending on which side they occupy. One side feeds into a filament, the other drifts toward a different basin of attraction. These boundaries define invisible borders in space, not marked by matter but by motion. The influence of voids and filaments means that massive attractors do not dominate their surroundings equally in all directions. Their reach is shaped by the cosmic web itself. Some directions deliver steady streams of matter, others remain comparatively quiet. Attraction becomes directional, channeled, and uneven. This perspective replaced the older idea of spherical gravitational influence. Massive attractors do not pull like simple balls of mass in empty space. They sit at the junctions of filaments, receiving matter that has already been guided, accelerated, and aligned by the larger structure around them. Motion near these attractors carries a memory of the entire path taken to reach them. Every bend, every acceleration, every slowdown reflects the distribution of voids and filaments encountered along the way. Flow maps capture this memory, turning galaxy motion into a record of the universe's hidden structure. Once this became clear, voids stopped being treated as empty background features. They became active players in shaping motion, speed, and direction across cosmic scales. Filaments stopped being decorative patterns and became the primary highways of gravitational influence. Near massive attractors, the universe behaves less like a simple system of pulls and more like a guided flow network, where emptiness pushes, structure channels, and gravity coordinates motion across distances so large that no single object can be credited as the sole driver. Could we discover something beyond dark matter? When we look at the universe and measure how galaxies move, we find that the motion doesn't match the mass we can see. Stars, gas, even the largest galaxy clusters cannot account for the speeds observed. For decades, dark matter has been the answer, an invisible, non-luminous substance that outweighs ordinary matter and dominates gravity on large scales. But the great attractor, the mysterious pull it exerts on our galaxy, the Lania supercluster, and the web of cosmic flows all push the limits of our understanding. They raise a question that scientists whisper about in corridors and conference rooms. What if dark matter isn't the whole story? The first clue comes from the patterns of motion themselves. Galaxies are not just moving faster than expected, they are moving in coordinated streams that stretch across hundreds of millions of light years. This is more than a local anomaly. The structures involved, the velocities, and the scale suggest that something massive is influencing matter in ways that cannot be explained by known forms of matter alone. Dark matter explains a lot, but some flows hint at subtleties that might point to something more exotic. One possibility is that dark matter is not as simple as we assume. The leading model treats it as cold, slow-moving, and only weakly interacting. But there could be hidden complexity. Dark matter might clump in strange ways, forming filaments or halos that don't match visible galaxy clusters. Or it could interact with itself, or with ordinary matter, in ways that produce unusual gravitational signatures. These interactions might create pull patterns that seem too organized, too strong, or oddly directional. Evidence from cosmic flows, from the Great Attractor in particular, could be the first signs of these hidden behaviors. Another possibility is that dark matter is only a placeholder for something even stranger. Modified gravity theories, like MOND, modified Newtonian dynamics, propose that gravity itself behaves differently on very large scales. If true, what we interpret as dark matter could instead be a signal that the force pulling galaxies is not the gravity we thought we understood. Under this idea, the Great Attractor would not just be a concentration of mass, but a test case for gravity behaving unusually across supercluster-sized distances. Evidence-based speculation here comes from observed discrepancies in velocities, particularly in regions where known mass is sparse. The patterns don't match simple Newtonian predictions, which opens the door to alternative physics. Cosmologists also consider the possibility of entirely new forms of matter. Dark matter might be part of a more complex dark sector, consisting of multiple kinds of invisible particles, each with different properties, some of which might interact or decay in unexpected ways. If these particles exist, their gravitational influence could create flows that appear anomalous, such as the coherent streams observed near the Great Attractor. Observing these effects doesn't require detecting the particles directly. Mass reveals itself through motion. But the fingerprints could be subtle, only visible in high-precision velocity maps, combined with lensing measurements. The universe may also be hiding large-scale structures outside our current observational reach. Dark flow studies suggest that galaxies in our local group move in directions that imply mass exists beyond the observable universe. If true, the Great Attractor's pull might only be part of a much larger story, with unseen structures stretching far beyond what our telescopes can see. Evidence here is indirect. Patterns in galaxy velocities that point toward regions hidden behind the cosmic horizon. But if further data confirms these trends, it could mean that gravity is being shaped by enormous structures entirely unknown. Structures that cannot be accounted for by dark matter as we currently understand it. Another layer of speculation involves exotic fields and forces. Some theories propose that additional forces, weak but cumulative over vast distances, could influence galaxy motion. These forces would not replace dark matter but complement it, modifying motion in ways that appear anomalous at scales like those surrounding the Great Attractor. The idea is that invisible fields might thread through space, subtly accelerating matter along preferred directions. The challenge is that these forces are hypothetical, yet their existence would provide an elegant explanation for why flows converge so smoothly along certain cosmic filaments while deviating elsewhere. Evidence-based speculation also looks at how dark matter interacts with itself. Current models assume very weak interaction beyond gravity, but if dark matter can self-interact more strongly, it could form dynamic structures, dense cores, transient streams, or even waves that shift over time. These structures would shape the motion of galaxies and clusters differently than a static, uniform dark matter background. Observed velocity deviations near large attractors could hint at these behaviors, suggesting that dark matter is not a passive scaffold, but a dynamic, responsive medium shaping flows in subtle ways. Some scientists even explore the possibility that our measurements are revealing the influence of unknown dimensions. String theory and related frameworks propose extraspatial dimensions. And although these are extremely speculative, gravitational effects from mass in other dimensions could, in principle, appear as unusual motion in our own three-dimensional universe. While there is no direct evidence yet, patterns in galaxy flows and velocity anomalies are precisely the kind of signal that might first reveal such hidden structures. The role of filaments and voids also intersects with these speculations. Dark matter, modified gravity, or exotic fields do not operate in isolation. They interact with the uneven terrain of cosmic structure. Flows along filaments could be amplified or guided in unexpected ways, depending on the properties of the underlying physics. Observed accelerations might therefore carry the imprint not just of hidden mass, but of complex interactions between matter, voids, and the rules governing gravity itself. Future instruments could provide crucial evidence. Surveys from the Vera Rubin Observatory, deeper infrared and X-ray mapping, and next-generation radio arrays will allow astronomers to trace motion with unprecedented precision, resolving subtle variations in galaxy velocity that could distinguish between competing theories. Each new measurement is a potential clue, confirming conventional dark matter, pointing toward a complex dark sector, or opening the door to entirely new physics beyond anything currently modeled. The Great Attractor is a testing ground for all these ideas because of its scale, its partial invisibility, and the extreme velocities it induces. Every galaxy streaming toward it carries information about the forces shaping its path. Large-scale maps, flow analyses, lensing studies, and velocity surveys collectively turn the Great Attractor into a laboratory for speculation grounded in observation. Even within the bounds of evidence, speculation is constrained. Any theory proposed must reproduce the coherent flows, the directional streams, and the velocity gradients observed across hundreds of millions of light-years. Random guesses fail immediately. Only scenarios that explain large-scale patterns without contradicting known observations are considered plausible. In this sense, speculation here is not free-floating fantasy. It is anchored by motion, mass, and the limits of detection. The stakes of discovering something beyond dark matter are immense, not just for understanding the Great Attractor, but for redefining the forces that shape the cosmos. If current models of dark matter fail to fully account for observed flows, then we might be glimpsing physics that extends beyond the universe we can see. Rules that operate on scales beyond our laboratory experiments, and structures or particles that interact in ways completely alien to ordinary matter. Each new piece of data adds layers to the picture. Some may confirm existing dark matter models, others may reveal inconsistencies. Either way, the evidence is cumulative, slowly building toward a better understanding of motion at the largest scales. In that process, every anomaly, every unexplained velocity, every unusual filament or void becomes a potential hint, a breadcrumb that could point toward physics beyond what we have imagined. The universe is leaving a trail in motion, and scientists are learning to read it.